Hi there. So welcome everyone to the summer school on data science. Olga, are you going to introduce?
Yes, I'm sorry. I just have like so many things going on at the same time. Hello, everyone. And as usual, good morning or good afternoon, regardless whether you guys are located. I'm really happy to see you all here at our summer school. I hope you can hear me well. Today is our last workshop for this summer school series, but I still want to thank our funders, Stifterverband and the scripts, and this is our, as I said, final workshop in this amazing first data science summer school series that was organized by Hertie Data Science Lab and by the Scripts Data and Methodology Center. And again, thanks to our funders for their generous support. And I just want to give a couple technical and organizational details. If you're on a Zoom meeting, and welcome everyone, both on Zoom meeting and on the YouTube streaming. If you're on the Zoom meeting, you're all muted and your cameras are off upon entrance. We do ask you to not unmute yourself and not turn your camera on unless you have a question. We do ask you to put questions in the chat. That way it's going to be easier to handle the questions for the participants and for the instructor and for the teaching assistants. If you're on a parallel YouTube stream session, you can leave questions in the live chat and we will help hand them as well as quick as possible or direct them to the instructor. If you want to speak up and you're on YouTube session, you can raise your hand and that way we will know that you want to speak up, and then whenever there's going to be a good time, you would be able to unmute yourself, turn your camera on, and be able to ask your question out loud. And I do want to remind all of you that the Zoom session is being recorded, and I actually need to start recording it. 1 second. Sorry about that. Of course, let me introduce this final workshop. It is Geo and Spatial Data in R. And I'm really happy to welcome Professor Ezer Pebesma. He's a professor at the Institute for Geoinformatics of the University of Münster in Germany, and co-editor of the Journal for Statistical Software and author of the R package SP, SF, and S2 and stars, an ordinary member of the R Foundation. And Ezer, the floor is yours. You can share your screen now and do the magic. And again, thanks everyone and welcome.
Ezer, your mic is muted.
Now you can hear me, right?
Now it's good. You're unmuted, yes.
Thank you. So thank you, Olga, for introducing me and starting and organizing this whole summer school, which is a very exciting event, especially since it is a free event and opened up for so many people. Now we are doing this. Now we're doing this online. So I'm going to talk about geodata and spatial data analysis with R, and the program is basically cut in 4 pieces. And we'll have a break at roughly at 12 o'clock, 15 minutes break. But I'm doing this in 4 blocks, so I will have 4 blocks of 45 minutes. And after each 45 minutes, I will take 15 minutes to answer questions from you. So I expect questions from you, really, either through the Zoom chat or asked live. Yes, we have time for that. We should have time for that. So a little bit of context. Let me just make my screen a little larger. So why do we talk about geodata and spatial data? So I think that this geo thing comes from Earth, but geodata is a rather unusual term. I prefer to speak about spatial data more in general, for the reason that not all spatial data is Earth related, or the Earth relationship is not always equally important. Let's say if people look through microscopes or so, they have Earth data, but the Earth coordinates are not so relevant. So we talk about data analysis because we are in a summer school about data science. The reason why I use R is, well, there are many good softwares that you could use for spatial data analysis. We use R because it's an open source environment made for data analysis and graphics that runs on all platforms. Yeah, so you should be able to run R or RStudio on your computer without any problems. And so there were some suggestions to do this in Colab, but I think most R users sort of, Colab seems to be more of an issue. And there's another programming language which is called Python, which has more installation challenges for many people. R is much less of a problem in that sense. Otherwise, I have no preferences for R or something like that. This is just that I've been involved in R for a long time and like to work with it, and it has a very sort of lively community of people that makes it really fun to work in that environment. People are very friendly and responsive. I put the link here to a book that we just pretty much finished in its first sort of complete form that I can go to now, which is called Spatial Data Science with Applications in R. You can see it has 18 chapters, and we are hoping that will be published on paper in 6 months' time or something like that. But it will remain online, available as an complete online source with R sections and so on. So how to use these slides? I'm not doing this from a PowerPoint for the reason that basically the document that I'm working from is essentially the result of a compiled notebook. Yes, it's the result from an R Markdown document that you find here. And I can now do this just briefly, sort of go to this GitHub page and then go to this document that I have here. You can see it. This is the document that I worked with, from which I created basically these HTML pages. You can click on raw here, then you get a raw file. There must be simpler ways of doing it. You could save that somewhere on your file, save it in a TMP direct, wherever. Yeah, replace that. And then you see it comes up here, and I can basically open that, and then it should automatically open with R Markdown. And in R Markdown, you can basically interact with this as if it were a notebook, in the sense that you go to an arbitrary R section, like here. Well, I won't do this one, but for instance, like here, and you can run this. Yeah, you can run it. You can see I ran it here. This is the R console output. This is the figure output that I got. You can also click knit, and you basically create the entire document. That takes a few minutes. So best to do it stepwise. If you're somewhere, and you haven't done something, what comes before this, there is this convenient button here that says, what does it say? Run all chunks above. So these code chunks are supposed to be run in order, not in random order. So they assume that the things above them have been executed. So you can run anything that is basically run above this, and after that, this one should be executable always. So that is now happening, and you can see that here we created just this figure. Yeah. So so that is how an R. So how do I get back to, yes, here? This is how I'm. This is how. How this works, right? So these are the steps to get you into sort of doing these things yourself. You need a couple of packages. There are actually 2 or 3 more than the list here, but RStudio will notify you that you need to install the additional packages. So what can we expect? So the program, as I said, I cut it in 4, which roughly follows also the order of the chapters in the book. I will first talk about spatial data and geometries, basically the basics of spatial data. What is so special about spatial data? What are coordinates? What should you be aware of when working with spatial data? Then I will talk about attributes. That means properties of points or polygons or raster cells, and how we deal with them in relationship to their geometry. And I will go through a pretty extensive example that uses the Gapminder data that you might be familiar with. Then in the third block, so that is after the 12 o'clock to 12:15 lunch, we will talk about data cubes and about larger data sets, about Gapminder data cubes, raster data, raster time series, image data cubes, and things like that. And then in the last hour, we will talk about models, so statistical models for spatial data. Right. So the first thing we want to talk about is just have a look at the chat, right? So if you have questions along the way, then you can either raise your hand or write them in the chat, and I can discuss it if there is something is unclear or I should do, or something technical issues, but also things with respect to data. So first we're going to talk about spatial data and geometries, right? So question is, what is so special about spatial data? Well, there's actually nothing special about spatial data. The thing is that if you think a little bit about it, data is about observation, and it's pretty hard to think about actually doing the act of observation without being somewhere, right? So we are somewhere all the time. So in that sense, that makes all data spatial in some sense, because the spatial location is essentially circumstances under which data was collected. Now that makes it then questionable whether this is very important, whether the data is spatial or not, right? Because a lot of data is taken somewhere, but that location is not so much of interest, right? If I'm undergoing a brain scan, then the location of the scanner is not important. But what is important is basically where my head was in the scanner, so that the doctor later on the images can figure out, like, where was this scan taken in this patient, right? So this is like spatial data, but the reference is the body, not the sort of location of the scanner. So it's not like earthbound, but the spatial information becomes body bound, right? So it's important, but it's different from usual, and this is also typically a problem that scanners sort of solve, and sort of it's very easy to solve. You don't have to discuss it very long. Another thing that's very important, of course, who was this patient that sort of went through the scan, right? That you get the right images with the right person when you look at information. Yeah, so that's another thing, which is somewhat spatially, but not really. If a person receives a positive corona test result, then the location of the testing may not be important, but it may be important for the person, whether to go in quarantine or not. If somebody, on the other hand, looks at contact tracing, then of course where the person was is very relevant. Yeah, of course, more relevant sort of who was the person near to, but where the near to means is basically a spatial relationship. So with spatial data, we mean data for which spatial locations or spatial relationships are, in any case, known and are having made explicit are part of the data, and for which they play a role in the exploration, in the analysis, or in visualization of the data. Yeah, so that makes a lot of data spatial, but also a lot of data is in that sense non-spatial, right? A lot of, for instance, data on web traffic or tweets that have not been, where there are no coordinates associated with the tweet and no place names and so on, or network data from social networks or something like that is quite often unspatial. Although there is a spatial process underlying it, it's not available. It's not. It may not be relevant. Now, how is spatial data represented in R? There's a lot of history in our data sets that have been there from the first days of R, and basically were there pretty much before that, in the days before R, in the days of S+, for instance. Here is a data set called Quakes, about earthquakes, which has a long list. The command head sort of prints the first 6 records of it, has a long list of latitudes, longitudes, depths, and magnitudes, right? And a station might indicate the number of stations that registered this earthquake. So the longitude and latitude are clearly spatial coordinates, right? We know about latitudes and longitudes, and depth basically adds a third. Latitude and longitude we could say as locations on the Earth, and the depth basically is sort of how close is it to the center of the Earth. So this is sort of 3-dimensional coordinates that we get here in a pretty special case. Another data set is the data set Volcano, which you can see if you ask the data set. So you don't even have to load it. It's just available for you. Volcano is a matrix, as you can see here. And it's a matrix where if I print the first 5x5 submatrix, so that is the top left corner essentially of this matrix, or maybe another corner, I don't know. Then we see these are just numbers, right? These are numbers of elevations of a volcano data set. And that's it. And we can then call image on the volcano and we get an image of the volcano. It looks great, right? So we see some kind of, from the basically the values are here being cut into equal intervals, and a continuous value scale is superimposed on that. It's just for that to visualize each of the cells. And then what we basically see by coloring each of the cells in their sort of their equal classes, what we then see is that we get these sort of contour lines that now, of course, follow the raster cells, so to speak, the matrix cells, and then we see basically the elevation going up, and here we see the volcano with the sort of with the depression in the middle, the crater essentially, right? So this is a very recognizable spatial data set, but it's just a matrix, that's all. Other data sets are, for instance, come as polygons, right, with coordinates. And here we have a very old data set that is from the library maps. And we take a subregion of that called Australia, and we say, don't plot it, but just make sure that the polygons are filled, and put the result in M. And M is then a list which has elements X and Y, and X and Y are the X and Y coordinates of the subsequent of polygons. And here we sort of put them into a matrix, and we see here the X coordinates and here the Y coordinates. And so these are, again, these are longitudes and latitudes, yeah, X and Y, longitude, latitude. And if we plot them, if we say map region Australia, then it automatically sort of creates that map and plots it. We see the map of Australia, which is essentially a sequence of polygons, right? It's one big polygon of the mainland, and then we have many small polygons that are associated to islands, and there might even be some polygons might indicate holes in other polygons, right? Because polygons can have holes in them. And if we see how that is organized, basically we get a string of a vector of X coordinates and then Y coordinates that we put here into a matrix. And you see that this matrix has rows with NA, which indicates this is the end of the first polygon and now the second polygon starts. Yeah, so this is a very sort of simple way of putting several polygons on top of each other into a matrix. You also see that the first coordinate is repeated in the last. Yeah, so this is a ring and it's a closed ring, meaning that the final point coincides to the first point, right? Which is the way to basically represent a ring in a two-column matrix. Yeah, so we have different ways in which this is done, and this is all sort of simple as long as you understand it and as long as you know what goes on. But it's also confusing in the sense that you don't know ahead of time whether this is latitude or longitude or whether this is longitude or latitude. Of course, here you can see it because numbers are outside plus minus 90. But if you would take a European data set, you would not see that. So all these kinds of little things are in there. And we will look shortly into a more structured approach to represent spatial data, which uses simple features, yeah, which is a standard that is now used in R a lot, but that is also available in all spatial databases in programs like Quantum GIS or ArcGIS, and also in many different environments. So it's a simple way that solves a lot of problems. If you look at spatial data, we immediately saw that sort of they consist of coordinates, yeah, to some extent, yeah. With coordinates, we typically think of sort of measures, sort of measured things measured along a ruler, and we basically think of a ruler paper where we have an x-axis and a y-axis and sort of equal divisions along x, equal divisions along y, and then we measure basically where we are in that two-dimensional space, right? So we would have two imaginary lines perpendicular to each other, called the Cartesian space, yeah, which is basically a flat space with orthogonal axes and equal units along x and y. Yeah, so if we have then 2 points, x1, y1, and x2, y1 in Cartesian space, we can compute a distance between them by this Euclidean formula equation that everyone should recognize, right? The thing is that the data that we saw here above, here, this is not the case. On this data, this is not the case. Here we have latitudes, longitudes, which are not Cartesian coordinates. Here we have actually some kind of a raster, but we see that sort of there is nothing useful along the x and y axis. They're just scaled between 0 to 1. So we just have the raster values. We don't have any coordinates where these raster cells are. Here again, we have latitude and longitude. So in many cases, this idea sort of brings us on the wrong, in the wrong direction. Yeah, that brings us in the right direction if we have projected data. But typically we have what we call angular coordinates. Angular coordinates are basically degrees. Here you see on a spherical body, the Earth is better represented by an ellipsoid, but it is so close to a sphere that you wouldn't even see it in a picture if I would draw an ellipsoid here. So what we see is we get a degree longitude, and the longitude, which is basically the direction, in the direction of the equator, and then either a degree north or south, that points you out the latitude, right? So these two coordinates are basically both angles. Another approach would be if we would take the same space as a three-dimensional space and say we have three orthogonal axes, x, y, and z, and we represent the same point by three coordinates: the x coordinate, the y coordinate, the z coordinate, which is the so-called geocentric coordinates. Yeah? They are used very rarely. They are used for doing things like conversions and something like that. But you see them rarely. What is more common is that we have two-dimensional sort of projections of an ellipsoid, and then use projected coordinates where we can do this magic with Euclidean distances, except that distances are distorted. When we try to have a curved surface and move it to a flat surface, we can only do that by destroying the distances that the original data had. Anyone who has ever tried to peel an orange and to make the peel of the orange completely flat knows that this is going to destroy the whole shape of the orange peel, right? So it's important to know that these kind of things, simple distance measures as we know them, as we would use them, Euclidean distances, are not relevant, are not the correct measure to work with if our data come in degrees, latitude and longitude. And it is really, this is data science problem number one that basically everyone sort of gets at some stage spatial data, and you see at some stage latitude, longitude coordinates, and you think, oh, okay, I'm going to throw this in my whatever clustering algorithm and see what happens. And something happens, but basically distances are computed there. Clustering those distances between points uses these kind of distances, which is essentially the wrong measure for longitude and latitude. So this is done wrongly a lot of time. So how do we solve this, right? Well, one solution is basically that of coordinate reference system. Yeah, it is similar to if you have regular data on measured quantities. It's the problem of what are my measurement units, right? If I have a weight, is this a weight in grams, or is this a weight in kilograms, or is this a weight in tons? Yes, if I have something, a rate per unit time, is it per second, is this per day, is this per month, is this per year, etc. Right? These kind of things is often, too often discarded, and leads to massive problems if you make something, if you make mistakes there, if you make the wrong assumptions. So coordinate reference systems are basically there to allow you to make the right assumption without having to guess. Yeah, they basically specify what coordinates mean, how they should be interpreted. Yeah. So I had here the quote from Moore. They are not just numbers, they are numbers with a context. Yes. Coordinate reference systems provide this kind of context for coordinates. So they provide a context for coordinates. They tell whether the coordinates are ellipsoidal, yeah, that means angles, degrees, latitude, longitude, or whether they are derived from that, or whether they're projected Cartesian coordinates. Yes, basically flat plane coordinates, typically in meters. In case they are projected, they also detail what kind of projection was used. Yes, there are different projections, and it's important to know which one it is, so you can basically go back to ellipsoidal coordinates, as for instance, from that projection, and relate your data set with some other data set by possibly going to another projection. So underlying ellipsoidal coordinates, there are always underlying ellipsoidal coordinates that they can be recovered. And in any case, they point out which ellipsoidal model, which datum was used. Yeah, we tend to think, or we pray often that we hope that this kind of definitions, once we know that this is longitude, that this is latitude, that we are done. Yes, well, stop believing that. It's not the case. The thing is that there are things called so-called datums that basically specify how we should interpret these coordinates. They're essentially coordinates on an ellipsoid. The thing is that there is not just one ellipsoid. There are many of these ellipsoids. There is the one that is used by most GPS systems called WGS84, which was established in 1984 and even updated a couple of times after that. So there are even several versions of that that solved a large problem in the 80s and basically made GPS much more accessible and useful and created other problems. And essentially we are now sort of 40 years later than 1984. And in the meantime, continents have moved. Yes, this movement is not massive. Yeah, it's not so large as sea level rise or something like that, but it is there, and in some places it is massive in cases of earthquakes or so. In any case, it's important to know which datum you have and how you can go from one datum to another datum. Yeah, so the datum is important, and there are more of them. So this is all about coordinates. So what is a coordinate? What does a coordinate mean? And how does a coordinate reference system tell you what it is? Yes, I can show you a coordinate reference system, for instance. Here, if I go to, if I take the coordinate reference system of EPSG 4326, which is the WGS84 one, we see that we basically say we define this thing by this little string EPSG 4326, where EPSG is the authority that defines that the coordinate reference system with this ID number has a particular definition. And then we get the definition, which is sort of a somewhat ugly block of text, which says, which describes the thing. I'm World Geodetic System 1948. I have an ellipsoid, and the ellipsoid is defined by these parameters. Yeah, these are the two parameters. This is the major axis. This is the flattening, I think. Yeah.
We cannot see your screen. We can only see your Chrome window.
Oh, thank you. That is good that you say that. Why is that the case? Let me just try to reshare my screen. Here it is. Yeah, I think I just shared my, right. Now you can see it, right?
Yeah, thank you very much.
Good. So I start here again. So I started R here. I loaded library SF, and then I said st_crs with this identifier, which says basically this is my authority. This is the organization that defines the coordinate reference system associated with this particular number. And you get the definition, which has basically the long name of this thing, and the two parameters, which is the sphere of the Earth, the size of the Earth it takes, the major radius, and which is a number for the flattening. Yeah, so how many meters is the Earth flattened when you compare south? When you compare the height, yeah, the distance between the south and north pole, and the width, yeah, distances between points on the equator on opposite sides of the Earth. Yeah, so there's 300 meters flattening. That is very, very few compared to the 6,000 kilometer radius. And it says a couple of other things like access order and its domain where it should be used. So that's an example of a coordinate reference system. When we know what coordinates are, yeah, that is useful, then we can start doing more useful things, and that is essentially thinking about geometries and thinking about measures, predicates, and transformers of geometries. We have geometries, and we use basically the simple feature access specification of these. And what we show here is the one for points, And this is basically a text representation. We just use that to print things. We don't use it to exchange things because text is not such a good exchange format, although the JSON people have different opinions about it. But in general, you should avoid it. But it's good to be able to read what's going on. So we have structures that are basically a point where we see a point followed by an X and a Y coordinate. But we could also have sets of points, which is a multi-point, where we have here 2 points, 0, 10, and 0, 1, and 10, 8. We could also have a line string. So you see again 2 coordinates, but the line string, basically the semantics of line string is that we have sets of points with straight lines between them. Yeah, and line string means line string, we can have multiple points. So if we have like 4 points in a row, then we have 3 straight lines between these 4 points that connect the 3 points that form the line string. Yeah, so this is a way to basically to approximate curves. Yeah, because they are not curves, they're straight line pieces. But if we make the distances small, sort of, we don't see that that they are straight lines. We sort of, it looks like a curved thing. Yeah, so anything like roads and paths and so on are represented by line strings. We can also have sets of these line strings. And there you see that we have here a single straight line, and here we have a single straight line, and they're not connected. Yeah, so this thing is not connected. This point is not. This point is not connected to this point, right? They are 2 line strings. And then we can have polygons, and here's a very simple one, which has 1, 2, 3, 4 points, where the first point, as we saw before, is repeated into the last point. So it's a ring, it's a triangle, it's a ring that closes. And to be correct, it should also be counterclockwise. I hope that it is. And it can also have several rings following it that indicate holes in polygons. Yeah, so that's why we have double parentheses here. We can, after the outer ring, we can have a set of inner rings that should be holes within this outer ring. Yeah, so polygons have room for defining holes in polygons. Similarly, we have multi-polygons, and that is basically a set of polygons, right? Similar to how a multi-line string is a set of line strings. And we can have combinations of these, which are sort of relatively rare to run into and inconvenient. If you run into them, just first thing you try is to get rid of them in some way, but which are geometry collections. They are there for a particular reason, that some operations should be able to return sort of mixes of things. Yeah, so all these things are basically ways of describing the geometry of a single thing, and we call that single thing a feature. Yes, and a feature is basically thought of as an abstraction or an instance of a real world phenomena. Yeah, so whatever, a road, a car, a tree, a house, all these kind of things, a city, and the simple comes really from simple, that we do a simple geometrical, we do simple linear interpolation between, sorry, not here, but here between points. Yeah, so we represent really sort of, you know, things that might be complex mathematical curves in reality. We represent them by piecewise linear things. Yeah, this is where the word feature and the word simple essentially comes from. Right. So then we can, as an example, we can read an example data set here. This is a data set that is basically read from the package, so that once you have the package SF installed, this data set is on your hard drive or whatever you're working from, and it's being read this way, so you don't have to mess with files and things like that. It's being read, and what we then see if we read it, and here these parents basically mean that read it, save it to NC, but also print it, sort of give the output of the print of it. We see a simple feature collection with 100 features. Yeah, so there's 100 records, 100 things, and 14 fields. Yeah, it says features because we have no clue still what the data set is. Well, the data set happened to be counties of the state of North Carolina, but of course we don't know because the data set doesn't tell us. But they are there. We see there that the geometry type is multi-polygon. So we have multi-polygons for that. We have dimensions x, y, that is the simplest. Yeah, so simple 2-dimensional coordinates. And we have a bounding box, which basically tells us the minimum maximum of x and y coordinates. And it says I have a geodetic CRS, and geodetic CRS means as much as we have we have ellipsoidal coordinates. Yes, otherwise it would have said I have a projected coordinate reference system. And it is associated to a datum called NAD27, the North American datum 1927, which is distinctly different from WGS84. Yes, it's a datum that has been established for North America and not for the globe, such as WGS84. So we have to think about, we have to take that into account, that if we sort of want to combine this with other data, that we may have to move this from NAD27 to WGS84, or use software that's clever enough to do so. And then we see the different fields, which is they're basically handled in a table. A table is sort of a modern reincarnation of a data frame, and it shows essentially the rows. The first 10 rows are printed here for where you see the different variables: area, the perimeter, which are measures of the geometry, and then the country, county ID, and the county name. Yeah, county name is here abbreviated, as you see. And one of the columns that's not shown here is the geometry, right, where you can see it's of type multi-polygon, which we already saw here, and which has unit degrees. Yeah, so it has a unit. Then we can, for instance, make a plot using ggplot2, which is not, not the easiest thing for everyone. So I'm not, I often have, well, I think I can now do this much of ggplot2, but I'm not a daily user of ggplot2, and then it looks often a little bit scary and so on. But there, it has a very nice sort of abstraction of the way you create plots and create actually very nice plots. So you can see here that the ggplot is created. ggplot comes with a geom called geom_sf, which has been specifically written to cater for simple features, so for spatial data, where the geometries come as simple feature geometries. And that basically takes an object of class SF and says, then how do you want to sort of have the colors filled? And I'm told it fill them according to this SID 74, which was the interest of this data set. It was 2 observations of 2 years, SID 74 and SID 79, of sudden infant death cases. Yeah, so these are disease cases over a 5-year period of a particular disease, sudden infant death. And they were, the worry was like, what's going on? Is there like a spatial pattern in these data? And can we understand the pattern in these data, and so on. And so this is an epidemiological data set. It's also a very old data set. It's one of the oldest, or a very old paper by, I think written by Noel Cressy, that distributed this data set, and that is why we still use it. Right, so I'm almost at the question and answers part. The first thing I want to sort of tell you is, before we go into a question, 15 minutes, or maybe if there are no questions, we can also think about taking a break. The main thing is that this looks nice, right? This looks good. We have these polygons. We see the polygons painted in gray. We see the sort of the values of the polygons, the sudden infant death cases, case numbers, with a nice color legend and so on. So what is wrong, or what is missing in this thing? One of the things that is missing is that we don't have a real control over this being a so-called coverage. Yeah, so for this type of data, you see a state and you see administrative regions, which are counties. But what you now, for instance, cannot see is whether one county overlaps with another one. Yeah, and this is, of course, this would be a crazy thing to happen. But if it were the case, you wouldn't be able to see it, because if I plot them, they're just, the last one just overplots the first one, right? So you wouldn't actually be able to see that. So these are just polygons, and I have 100 of them, and we have to trust, the creator of this data set, that this doesn't happen. Yeah, but there's not any guarantee or something like that. They're just 100, records in a table here, and each record has a polygon, and we have no clue what are the constraints on these polygons. There are no constraints. Yeah, they're just polygons, and they should be valid polygons in the sense that they shouldn't self-intersect and that holes shouldn't be outside of the polygon and stuff like that. But there are just 100 individual items, whereas the data set we have is a state with counties. So the sum of the counties should be identical. The union of a county should be identical to the state, and no county should overlap with another county. And there should also not be little holes between them. Yeah, so it's mean that the sum of the counties should be identical to the state, meaning that there shouldn't be like little gaps that you wouldn't see by plotting them on this scale. So that is the idea of basically of a coverage. Yeah? So a coverage is essentially a higher level concept. That's the tessellation, it's the subdivision of a particular space into regions, yeah, where it's made clear how every point is uniquely assigned to a subregion. And the thing that we don't have this here is that we cannot see whether there are little gaps that are too small to be seen on this screen. We cannot see that. We cannot see whether there are overlaps. But even if this data set was entirely correct, but provided this way as like 100 polygons, we have the problem, or we might have the problem at some stage, that points that are on a boundary between two counties are actually basically on the boundary of both counties. So then comes the question, how is that point assigned to a county? Yes, because the coverage means that every point is uniquely assigned to a subregion. Now, if a point is on a boundary of two polygons, there is no way of uniquely assigning it. Yeah, there is just no way of doing that. So that is basically a higher level concept that says I have a region and subdivision of the region that you cannot do with a set of polygons. Yeah, so then comes the question, why do we always handle these kind of data with sets of polygons? Well, the reason is probably that this is the easiest and the problem is not large enough. Yeah, so nobody gets really into troubles, because if the data are okay, then they're okay, and quite often they are okay because they come from some official instance, and it's probably too hard to do it the other way. Yeah, that is and that's a fair deal. So if you work with a proper GIS, a proper geographic information system, such as GrassGIS or such as ArcGIS, then they will have what they call topological models, which means that we don't store counties as rings, as polygons, but we basically have really sort of nodes and edges in a table that says what is left and what is right, and how do I assign points to the left and the right? How do I assign points that are on the polygon, for instance? What do I do with them? There are different. Yeah, there is a question that I can now go into. So can we entirely trust these maps when trying to obtain causality inference for some purpose? Bitan, yes, that is a very good question, but I need to know more context what you mean by causality, because causality is, so if I sort of cut your question back to the sub-question, so can we entirely entrust these maps? Causality is a difficult subject in statistics, in science, everywhere. If we go back to sort of question, can I trust this map? Then as a data scientist, you always have responsibility. Yes, so the responsibility is basically that whenever you take on data, yes, that you have checked that this data is the proper data that you need, and this data is essentially correct, quality controlled. For administrative regions in general, it is for large parts of the world, it is relatively, I think it is relatively easy to get authorized data sets. Yeah, to get basically data sets from the administration that defines where property lies, right? Where administrative boundaries are. Of course, there are versions of things. There are disputes about countries. For instance, if you have counties, if you have conflicts and so on, disputes about what is a country. We'll look into that later. But you should basically go to the best and the best sort of instance that could give you this data, and use the most recent instance of the data set, or of the proper instance of the data set that is needed for your purpose. Coverages are there basically in GIS. A much more common coverage type is that of raster data, yes? which basically rasters are a different way of cutting up space, but they do that by regular tessellation, and in this case by using square or rectangular pixels. Yeah, so this is also a very common case in data sets. We have seen it here in the volcano data set, where basically anything was missing except the values of the raster cells, so that's what we plotted. But in general, we basically do this more cleverly. And for instance, here is a package called stars, which nicely builds on top of SF, but also deals with raster data and reads a raster data from a so-called GeoTIFF here. So this is a GeoTIFF that has a piece of a Landsat 7 ETM sensor. So that is a satellite and has this data for a region in around the city of Olinda in Brazil. And here you can see the ggplot of this thing, which looks a bit more complicated, but where you see basically this data set comes with 6 bands. 3 of these bands are RGB, red, green, blue, and a couple of them are other colors like ultraviolet or near infrared or infrared. So we have multispectral data. So this is all one image, but basically cut up in 6 pieces of the visible and invisible spectrum. And we see basically an image, right? An image as we know it, but an image that's georeferenced, where we have coordinates. These are X and Y coordinates. They're very different numbers, and you can see here that these are coordinate reference systems from UTM zone 25 south, right? So that is a universal transversal Mercator projection in a particular zone on the southern hemisphere. We can get a longer description of that, but this is essentially enough to understand, okay, UTM zone 25 south is a proper projection for this area, and they are UTM. So another plot we get here, if we say simply that the base plot method, which shows uses a little bit more of your screen estate to show something, and also uses gray tones. It uses a different color breaks that are basically, that does some histogram stretching, or you could say high dynamic range tricks to basically blow up the information over the better distribute them over the color, the available colors that you have. Yeah, so these are raster data, and raster data are coverages in the sense that you could see things, you could see raster pixels as little square polygons, but they're actually not. Yeah, we can also convert them into little square polygons, and then we have a simple feature representation of the raster with the problem of lines that are basically owned by both polygons. But in a raster model, actually we have each raster cell contains only its top left corner, right? The other 4 corners are contained by other cells, are contained by neighbor cells, because it has 4 neighbors. And also each raster cell only contains its top side and its left side, and not the right-hand side and the bottom side, because they are contained by other neighbors. Yeah, so these are kind of rasters cut up space in a way coverage does. Good. So we are at the end of the first section, and the next section I will start talking about attributes at 11 o'clock. And I'm looking forward to having some questions. Yeah. So we looked in the causality question, and there Bitan continued. For example, when using these maps for understanding people's behavior or some statistics which might be depending on demographic boundaries, can we assume that one polygon is not overlapping with the other? Yeah, that is a very good question. And actually, you don't have to assume these things. You can actually pretty simply check these things. There's that I'm not going into exactly explaining how to do this, but that is being explained in the book that we have. We'll go there. which has a somewhat longer chapter on geometries. And there you can see that there are a large number of, here we see these geometries, a large number of operations are being defined for geometries and also for pairs of geometries. Let me see, operations on geometries. Yeah, so there are operations in 3 classes: predicates, basically saying that something is true or false; measures, which give a number; or transformations, which generate a new polygon. And here we need to go to the binary predicates. Yeah, so binary predicates. So the question is whether 2 polygons that look as if they are, you know, side by side, whether they overlap or not. And that we can do with the binary predicate. List of binary predicates is here, and there is there are several predicates. For instance, like the predicate overlaps. Yes, that means A and B have some points in common. The dimension of these is identical to that of A or B. Yeah, so A, and so the dimension means 0 for points, 1 for lines, 2 for areas, right? So if A and B are 2 areas, and they have some points in common, and the points in common are a 2-dimensional area, or the same dimension of A and B, then we have an overlap of these 2 polygons, right? So we could then ask, for instance, here for this data set, which I'm loading now. Here, this data set is which we just had. Yeah. Oh, this is going to the other screen, but I'll drag it here. We could now ask, do I have overlaps of NC with NC? Yes. And then we see that polygon 1 has 0 overlaps with other polygons. Polygon 2 has 0 overlaps with others, etc. Right? So I could ask for the lengths of all these elements, and then you could see that if I type correctly, the lengths of each of these vectors, and then you can see that they are all 0. Yes, so now I checked that I do not have overlaps between any pairs of polygons. Yes, so that is good that we can check. Yeah, we should check this. That is a good check. What we have not checked by this is whether we have gaps between them where we shouldn't have gaps. For instance, small gaps. And these gaps can actually happen. Overlaps can also happen this way, but gaps can happen when you have a very complicated polygon, yes, with very many points, basically discretizing this polygon. It makes the data set a very large data set. So what you could do is generalize this polygon. It's basically throw out points that are, you know, nearly on a straight line. Yeah, that is called generalization. So we can generalize each of the polygons. But if 2 polygons have a boundary in common, right? And you're going to generalize the first one, and then independently you're going to generalize the second one. The boundary might not any longer be a common boundary, right? There might be gaps between them. And these gaps is a very common instance that are very hard to check. Yeah, we don't have, let's say we can check overlaps, but there's not like a topological predicate that says, do these 2 boundaries have a gap or something between them? Yeah, that's much harder to do. So overlaps are relatively easy, gaps are harder to check. And when you can do checks, you should do checks. Yeah, you can do checks. So read this chapter. Can ArcGIS be integrated with R, or is there a way to work with them together? Yeah, that's a good question, actually. I think that you can. They have some kind of a project, and I forgot actually. It's called the R Bridge, ArcGIS R Bridge, and you can essentially, they made it simpler to move ArcGIS data into R, do computations in R, and get your results back into ArcGIS, for instance, to create a map. Yeah, so there is a product that they do that. I think they just did it because customers wanted it, because there was functionality in R that they didn't have in ArcGIS, and they wanted to integrate that without entirely moving to R. It's essentially Well, the thing is, ArcGIS is a closed source platform. So if you do data science and you take the science aspect of that seriously, then essentially you should do things with open source platforms, right? And ArcGIS, well, if you only use it for maps, I don't know. I'm the wrong person to ask that, really. So, but yes, these things can do, and they're basically developed by ArcGIS to, to make sure that not everyone runs away from using ArcGIS. Marcus, Conrad. I'm often using epsd.io to find out suitable CRS for my region of interest and purpose. However, I find it often difficult to choose a coordinate reference system because there are sometimes so many of them, and sometimes I find none for my specific needs. For instance, an equidistant projection for a certain region. Do you have any tips for that problem? Should I rather specify my own projection using the proj4 string? Yeah, that is a good question. I don't think, Marcus, that there is a silver bullet. The thing is that whenever you do a projection, you have to compromise on something, right? You basically lose the original relationship between points. So you can preserve some things. You can preserve areas, or you can preserve directions, or you can preserve some distances, but you can never preserve all distances. For instance, you can preserve distances to a particular point, but not between arbitrary pairs of points. So, and whenever you choose one of these, then you compromise on the other ones, right? So if you keep shapes and directions like the web Mercator does, then basically you lose the equal area property, right? You get these terrible maps where Greenland seems the biggest continent on the Earth. And Antarctica is missing because it doesn't fit on that projection. So there is no silver bullet, and there is essentially the thing that you need to think about, like what is important for my purpose. Projection is always about visualizing things, and if there's anything where countries are involved, then I think equal area projections are really a must-go. There's also my use R keynote that I give this year, where I give a couple of examples of doing that. Good. So we're 11. Are there any further questions about geometries? Yes, these were good questions. Thank you very much for that. Right, so there are overlaps. There are measures like I can compute the area or the length of a line string. Then there are all kind of transformers. You can compute centroids of centroids of polygons. You can compute buffers around lines or around polygons. You can do all kind of things. Convex hulls around points. There are intersections, unions, differences, and so on that you can compute. And there are things like n-ary differences, intersections, and things like that. Good. So you obviously see, right, that there's a lot of the information that I'm explaining to you now that is also in this book. And the book takes a little bit more than 4 hours, I think, to go through, but might be a point of reference for if you are looking for particular problems or solutions. Look especially for it to find out about problems. Half of the work of data scientists is to understand problems. What are the problems, and why are they relevant, or why are they not relevant? Understanding why certain problems are relevant or not. Okay, I was going to go to the second section. Right, we had the questions and answers here. So we go to attributes and to support. So now we go into the next chapter of the book, leaving the coordinates, the spherical projections, and so on, the geometries behind us, and operations on geometries. But going to the next section where we have properties of geometries. Yeah, and there it gets really exciting, because that is basically the flesh and bone of spatial data, is that we have geometries, but we know something about the geometry, right? We know there is a thing, there is an administrative region, and we know that there is, for instance, a particular voting result or a particular disease incident or something like that that's happening, and analyzing these data basically in relationship to their spatial properties is of interest, right? We could ignore anything. We could just run an analysis on the table of whatever, you know, counties and disease data, ignore that these are spatial. But then the question is like, oh, yeah, maybe there is some kind of spatial effect. Well, what are the spatial properties here? So we call these things attributes. Yeah, so we have feature geometries on one hand, and the other hand feature attributes, which are the non-geometrical properties. Then there's of course also time, which I would not say is an attribute. A lot of GIS consider it an attribute, but it's a bad idea. Yeah, it's basically time is as much a geometry as coordinates is a geometry, right? It's really, it's things are happening in space and time, and then we measure things and their attributes. A crucial consideration here is to consider support. Yeah, support or footprint is a term that is not used enough, and that people don't understand sufficiently. Yeah, because it is basically decisive and very important. If we have anything that is not a point, if there is anything that is not a point, but it's a line, line string or multi-line string or a polygon, and we have an attribute to it, then we need to think what this attribute means. If we have a line string, it basically means we have an infinite number of points, right, on that line string. If we have a polygon, it's much easier to think that this is an infinite number of points within this polygon, right? So this infinity is really means, you know, it's an infinity, right? It's a very large number, any point. So it's a continuous space, so there are an infinite number of points. So if we then have an attribute for such a geometry, the question is really, is this attribute valid for each of these points, right? Meaning that we have a point support attribute, or is this attribute valid for the collection of the points, right? And this is an important thing to think about. An example of point support is, for instance, we have a polygon that is a soil map that delineates all the sandy soils, right? That suggests, soil maps are of course never 100% accurate, because this is very difficult. You cannot look the soil everywhere. But this map really means that within this polygon, right, anywhere you go within this polygon, you're expected to find a sandy soil. Right, this category, sandy soil, is valid for every point within this polygon. If, on the other hand, an example of the area support, if we have an administrative region and we have a number for the population or for the population density of that region, then this is not a measure for every point in that area, right? It's a single number. For instance, population density is a single number. That means if you go somewhere in that polygon and you would look at the vicinity and how many people in that sort of smaller subregion live, then that will not be identical to the population density, because the population density is an average, is a count of the whole area divided by the area, the total area. So it's a count over a total area. It's a single number. And nobody expects that this will be continuous. There will be always, in larger regions, areas that are more densely populated and areas that are less densely populated. So this is a number that is really associated to the area and not to smaller subregions and not to points. Of course, at a point, nobody lives. Nobody can live at a point. We all need more space than a mathematical point which has zero size. So the point support is an abstract thing, but and also for soils, of course, you cannot really observe. You cannot observe soil at a point, but you can observe soil at something that is, 10 by 10 centimeters or half by half meter if you dig a hole. And of course, for densities or aggregates or counts, you can do this for smaller areas. When we analyze area support data, so aggregated data, and we choose a different set of polygons, that leads to different results. Yes, and that is a very sort of difficult proposition to understand that and to realize that. And that is a problem that is well known already for 50 years, for as long as we do these kind of things. And it has many different names. One name is the modifiable variable unit problem. There's even a Wikipedia page that explains it. The other is ecological fallacy, they call it. There are different names for this. If I do my analysis on the county level, it gives a different result than do I do it at a state level in terms of relationships and correlations. They can entirely flip sign. And there is also the sort of the activity of intentionally manipulating polygons such that particular analysis results is obtained, and we call that gerrymandering, right? So this is a certain areas of the world where, you know, people do a serious job to sort of you know, turn democracy in their preferred outcome. They do that. And it's relatively easy to do. There's even R packages that can help you do this to find optimal delineations of voting districts. So a common operation. One thing to keep in mind to think of: do I have area support? Do I have area support? Do I have point support? Is the polygons that you look at, right? The polygons you look at on the soil map are really kind of thought as boundaries between soil types. Yes, they are the result of mapping the attribute. Yeah, this is the same thing with land use. If you have a land use map, then the polygons of a certain land use is not like somebody drew that polygon because it was a fun polygon to draw. No, they drew it because there one land use changes in another land use. There's a boundary between them. So the boundaries are associated with the attribute. Yeah, it's a result of mapping or maybe image classification, whatever you used for mapping. For most area support, so a lot of socio-economic voting data and so on, the boundaries were not designed for that purpose. They were these boundaries for counties or states or countries, whatever, were not put there to map population density. No, they're just used because your data is collected at that administrative level, right? Data collection happens there, but it's not that this boundary is meaningful for population density north and south of the boundary. They're not result of mapping the attribute. Yeah, so that's a good thing always to keep in mind. Where do my boundaries of the units that I'm looking at, where do they come from? Do they have anything to do with the phenomenon I'm looking at? I'm looking at sudden infant death cases, on disease cases. Were the boundaries of my units kind of a result of mapping this disease? No. Okay, then probably I have area support, and probably I have this modifiable areal unit problem. A common operation on spatial data in general and aerial data in particular is to generate attributes for a new subdivision. Yes, think of lekker dankje. Think of yeah, you are asked to do an analysis on a very fine administrative region, and you're being asked by somebody to say something about effects of expected impact of climate change. Now you have to get climate change data, and these climate change data come from climate models. Climate models discretize the Earth with a raster, with a grid, and you get some grid data, you know, with units, small, hopefully small units, maybe large units, that don't correspond to your target spatial units, right? So you have to, from these units, some kind of model result, weather, forecast, climate, whatever, you have to go to the units that somebody asks you to make expressions about, right? And that is, of course, associated with uncertainties and with errors. And there are different things you can do. There is chapters in the book that sort of points you to simple things you can do. There are also very complicated things. The activities, depending on which way you go, are indicated by upscaling or downscaling. Upscaling basically means that the new units are larger than your original units. In that case, you're typically lucky. Yeah, you have a lot of raster cells and you think, okay, well, let's take whatever the mean or the median or the maximum. Or you go downscaling where you have a very large for instance, a very large raster cell in a small region for which you have to make an assessment, right? And that is typically statistically a much more much more complicated thing to do. When you do this, there is also a chapter in the book about that, is you need to take into account whether your variables extensive or intensive. Already mentioned in this example of area support, you can look at population density, right? Or you can look at population counts. Population counts would be an extensive variable in the sense that if you split a state with a number of people living there in two halves, then the population is redistributed. Yeah, maybe it's cut in half. If you have no clue, you would sort of use the areas to weight it. If you know more about it, about population density within the state, you would do a more clever activity, which is called asymmetric mapping, for instance. But in any case, you would go to something where the sum is being preserved, where you don't get suddenly out of your analysis, you end up with a larger total population. You would preserve the total population. If, on the other hand, you have an intensive variable, such as population density, then you might as well try to preserve the mean. Probably the really good approach would be to go to population to do the proper analysis there, and then again to population density. But you might have variables where you can't do that. For instance, variables that are also extensive, like temperature, right? Or like elevation. Yeah, you can't look at, there's not a total temperature or something like that. You can't do, you can't go to a count there. But these are variables that are basically not, by themselves are not extensive in the sense that they don't represent a count or a mass or a length or something like that. Right, so these are important things to keep in mind when doing analysis that involves upscaling or downscaling.
Edzer?
Yes.
There is a question. Is there a platform similar to Eurostats that contains data for coordinates for different regions?
There is not like a single platform for doing that. There is just many different activities and platforms. So Eurostats would have the official NUTS 1, 2, 3, 4 level boundaries, right, for European countries, but may not have that for the entire world. I think Eurostat also distributes world coordinate, world, I remember there was something called GISCO or something like that, a world boundary data set. But there's not like a single global one, like something from the UN. Of course, the UN has, has many different organizations that all use spatial data and also try to coordinate things. But I don't think there is a single platform. There are just many platforms, and some of them are more authoritative. I think Eurostats is a relatively authoritative, although these are also just researchers trying to do their best, the best they can, with the usual limitations that anyone has. Yeah, we will look into a few examples coming up when the issue is world countries. Right. So good questions. Thank you. The Gapminder example. You may have known of Gapminder, you may not. Gapminder used to be an essentially software that would run in browsers like 10 or 15 years ago, and a collection of YouTube videos by Hans Rosling that if you have never seen them, you should definitely look one up. Hans Rosling, I think he passed away a couple of years ago, but had this, this very nice way of explaining sort of what is happening with the world and with life expectancy and welfare, how the world is developing, and basically had a relatively optimistic message that a lot of things are developing in a very positive direction, and definitely if it is about health and life expectancy. He also was very early with distributing the data sets that he used. He used, of course, data sets that to some extent were, redistributed, were obtained from the World Bank. Yes, World Bank is here an interesting sort of instance that distributes global country-associated socio-economic data. But he would also, I think he would also use different sources. But the Gapminder website would always have a copy of the data set that he would use. And I now found this Gapminder R package, which was written by Jenny Bryan, a very highly esteemed data scientist working for RStudio. And it basically says, well, there is in this package a data set called Gapminder. And by continent, it explains which country we want to sort of find out now by continent, which country experienced the sharpest 5-year drop in life expectancy and what was the drop. So by continent, we want to find the country with the sharpest 5-year drop in life expectancy, right? So here's a composite spatiotemporal question, right? Do something by continent that is spatial. We want to find the country. Well, country are the units of Gapminder. Sort of the observations are country-based, but we want to sort of find the sharpest 5-year drop in life expectancy. We have records of life expectancy, and we want to see a drop in life expectancy. So we want to look at basically differences, from one 5-year period to the next 5-year period. The frequency of the data is 5 year. We want to find the sharpest drop of that. And she says that this is her analysis, right? She says that this is the way you can do this. So you need, of course, the dplyr, the RStudio workhorse data analysis package. We need to load Gapminder so that we can directly use this Gapminder object, which is like looks like this. It has 7 columns. It says the country, the continent, the year, life expectancy, the population, GDP per capita, and this is something that I added, which is we will come back to that. So it has 6 columns. It says then you can do this by group by. So we group by continent and by country. So we have a sort of a 2-level grouping. Then we select these 4 variables because those are all the variables that we need. Then we compute the life expectancy change, the life expectancy delta, as the difference between life expectancy and its previous observation. The lag operation takes observation in a vector. And then we summarize that and we say the worst change, lagged life expectancy is basically the minimum of this whole sequence, where we have to remove missing values because lag probably creates missing values, right? Because you have, when you have 10 observations, it can only, it shifts them. And so it has to add an NA to the start or the end. And then we filter this, and we filter this by saying that the worst LE delta, worst life expectancy change should be smaller than 2. And then we arrange by the worst life expectancy delta. Where I'm trying to think what this does. I think I understood it. The rank, the minimum rank. Yeah, so here we, if we take the minimum rank smaller than 2, we basically get the largest value. We get the largest negative value. Yeah, so we get the we get the observation with the largest negative change. And then we sort the resulting. We sort the resulting table by increasing change in life expectancy, right? So then we get these 5 continents that we have in our data set. You see, we don't have all continents, and per continent we get the country with the largest drop in life expectancy. And we see a couple of things where kind of, understandable in the sense of historical events. And then I thought, this is such a great, composite spatial temporal question. Can we also like get a map of this? Typical data science problem. Yeah, somebody showed a great table. Can you put it in a map? Well, we could put this, these 5 numbers in the map. The thing is that I want to put this data set in the map and sort of map aspects of this data set that basically are intermediate results here, any of them, and explore what's going on. And interestingly, when you do that, you can, it is pretty hard to do that from here, because what we have is spatial information essentially in the form of labels, country names in the form of continents. Yeah, so I'm going to now try to match this to country polygons. Yeah, what we need is a polygon of Afghanistan to draw Afghanistan on the map with a certain life expectancy associated with a color in that map, or maybe a change in life expectancy. We can do that later. I tried to do that, and it was a bit of an adventure, in the sense that you then get into the nice problem that Afghanistan probably will work, but will they all work? Yes. We have, you could already ask, like, how many countries does the Gapminder data set have? 142. If I think of the number of countries of this world. Anyway, we try this. Here I used the library Natural Earth. And Natural Earth has a command called any Natural Earth _ countries, which comes with a relatively generalized version that plots very nicely on world maps. If you would zoom in on particular smaller countries, it's pretty rough, but that's because it doesn't want to, this is a generalization problem again, right? It doesn't want to be a massive data set that takes 5 minutes for every world map to plot. So we get now natural countries. Natural Earth is also a data set that provides country data and also some kind of country statistics that tries to be as open and transparent as possible in respect of how they collected these data and where they come from and what they did to it. Yeah, so that's a very good effort. Quite often you download for somewhere a data set and have no clue how it was constructed. Yeah, so think of the get data, the GADM data sets that are used a lot, where basically any information about provenance or where the data set or authorities or so come from is absent. I didn't go into much detail in what they provide, but anyway, it's an interesting data set and it looks like being useful. What I try to do here is using the R command match, which does a match between the country's name in Gapminder and the administrative names, which is the country name in this NE, the Natural Earth country data set, right? And then I get matches, yes, but I also get missing values. So this I can I can basically do that here. This goes pretty fast. You can see if I look at the match, so the matches basically are the indexes, right, of the first data set to the records in the second data set. Again, the second data set, Natural Earth, has much more countries. It's only 1 record per country. Has 177, but you see a lot of missing values. So we have countries that don't match up. Yes, and if I look then at which countries in my source data set, right, are missing value when I try to match them to the target data set, which has the polygons, yeah, then I get sort of all the problematic countries, yeah, and you see that these are the problematic countries, these 19, yeah, and that already, you know, gives you some idea about, you know, what are spellings of country names, how are country names spelled. For instance, if you see Korea, dem dot rep dot, then I immediately think, oh, well, it's probably in the other data set, it's probably Democratic Republic of Korea or something like that, or, you know, without being abbreviated. If I see Cote d'Ivoire, Ivory Coast, maybe, yeah. So there's already some, you know, some suspicious United States of America, yeah, rep dot Yemen. So what I did, this is pretty ugly, I said. And the only thing I could think of is to solve this the hard way, basically by hand. Yeah, looking at, you know, text matching of things. I didn't do a good job, and you will certainly, if you spend time, do a better job in doing better matches. Yeah, but what I in any case did is I have these sort of the missing, you know, these are my missing names in Gapminder that I want to fill up with NE. So I use that, and then I use sort of the new names, which are the names of the countries in my natural Earth, and I match them one by one, basically by search, by stupid text, well, by text search, right? And I think you all are much more experts in text search. I think you had a course also on analyzing text data, which is a very exciting thing. But anyway, you needed to match there. These are the matches that I could find. Yeah, so here in Gapminder, Congo, dem rep is written out. Democratic Republic of Congo in the natural Earth data set, right? So we can, this is English, Ivory Coast. This doesn't have a hyphen. So we have a couple of matches here. Yemen, rep is called Yemen. United States of, is called United States of America. So, so I did some, I think I did some ugly, well, some kind of string replace all. I had to go to, I don't do this often, so I really had to go to actually to Stack Overflow to find a recipe to do this sort of multiple, text replacement, right? Sort of, here are all the things I want to replace. I want to basically replace all these instances with all these and all these with these and so on. So you can do that with str replace all, which is part of the stringer package. And then I did a match again, and I ended up with a much smaller data set that is that are countries that are not available in natural or that I couldn't find. Yeah, and these might be areas that Gapminder actually identified or recognized or said we have data for these area and we are including them, but they are not, you know, they are not by everyone considered as legal countries in some respect. Yeah, they might be considered legal by some, or independent countries by some, but not by everyone. So, you know, West Bank and Gaza, is that a country or not? I wished it was. Singapore, similar. So, yeah, so we end up with a couple of doubt cases and differences in politics between Gapminder and between natural Earth. But in any case, for 11 countries, we were able to assign the proper values. So what we now can do is using this newly set of matches. Yeah, we have a new set of matches with the after we replaced. Basically, I created here this N country, the new country name in Gapminder. Yeah, that is what you saw here. This is my variable. Yeah, Afghanistan remains Afghanistan, but Cote d'Ivoire becomes Ivory Coast and so on. My new country label, that is a better match. and I obtain basically the geometries from natural earth using the indexes from the match, and then get basically a geometry column for Gapminder. Yeah, so now I have Gapminder with geometries, and the geometries are multi-polygons obtained from natural earth, and I have 1700 features, which is of course much more than 100. What was it? 140 countries. But that is because I have 5-yearly measurements. The time series are in a column. Yeah, we know that the time is basically space is in a column, but time is also in a column. So we have repetitions of every. We have repetitions of every country in a long column, in a long table form. We can then, for instance, right? What we also see, of course, we still had missing values, right? Those were this set of countries that we couldn't match, and when we fill that, and we have a number of NAs, what we see is that we get 96 geometries that are empty. I didn't discuss that, but the empty polygon or empty multi-polygon essentially means that I'm a multi-polygon, but I don't have any points. Yeah, it is basically it has the role of a missing value in a geometry. So this value is not null or NA or something. It has a specific value in the context of the simple feature specification. It's a multi-polygon empty. Yeah, so these things exist. Yeah, multi-polygon empty is a multi-polygon with no point, with no polygons. Right. So they are mentioned here. They are empty geometries, and we can filter them out by the st_is_empty predicate that tells you whether the geometry is empty. So you can get rid of them if you want to, but they're still in here. If we throw things to a plot command, they're simply ignored, right? They're considered as missing value. Here I take the geometries of the Gapminder extended with geometry, so the Gapminder dataset with SF thing extended, and I plot them, which is just gives the boundaries. And then I said, oops. Yeah, so this is the country, the world map of the Gapminder country dataset that we look at, right? And this is something that we, that we were not really aware of when we looked at this analysis, right? Here we started with Jenny Bryan saying, I created this Gapminder dataset, and now I'm doing this analysis, and these are the steepest drops in life expectancy. But where does the dataset Gapminder come from, right? Apparently, the Gapminder dataset doesn't include Russia, for instance, right? And so I didn't do this. I didn't color this, but there might be other countries that are entirely missing. I should have colored the countries essentially to see whether there are gaps in the countries in the sense of countries that are missing. What she did to create this, what she created to create this dataset is quite extensive, and all the scripts are in the Gapminder, part of the Gapminder package, or in any case findable on the GitHub site where she maintains this, and so you could repeat them step for step. And actually, these steps are part of the teaching course where she explained like what you have to do to clean up a dataset. But the main thing is essentially that she created countries. She selected countries with complete time series, right? So this Gapminder dataset has time series for some years that are yearly, for some years that are 5-yearly, but for a number of countries there are sort of incomplete datasets, and these incomplete datasets were clearly we're basically dropped, right? That is why we're looking at 142 countries where where natural Earth has 177 countries. So what she also says, so this is not like hidden, but this is something that you wouldn't immediately see when you look just at sort of tabular results when you start off with this Gapminder dataset, which you trust, which you would trust. She also writes in the documentation, the supplementary material, the supplementary data frame Gapminder unfiltered was not filtered on year for complete data and has 3,313 rows. Yeah. And then I said, maybe we should use that. So that is apparently the entire data set. So this is over 3,000 rows. We only have 1,700, so we have half of the records of the complete data set. Yes, and we don't know exactly what went on. So I started now doing the same thing, using Gapminder unfiltered, and created this new country name where I did this match, and then looked at the country names where I had still missing matches. Yeah. And now you see that I still have 25 missing matches, yeah, which is, of course, a couple of countries were entirely thrown out. So I can, in principle, I should actually sort of start again and look for all these countries. So we have 25 rather than 9 that we can't match for natural Earth polygons. So I should really sort of start again and look for all the new ones in this list and see if I can match them. But I think I didn't do that. We can add the countries here in the same step, basically by adding the sort of the matched geometries of natural Earth to this unfiltered Gapminder data set, and then we end up with 215 geometries empty. Yeah, when we plot that, we see that in any case that Russia is plotted. Again, looks much better, I said, but that looks much better essentially because the difference is Russia, right? It's such a big gap here that you see that you wouldn't, but there might be a couple of countries as well here that are not present, that we, that would be, you would have to look at to sort of basically plot the differences then see it. We could see which other countries are now included but absent from Gapminder. We do this by a set diff. Yeah, set diff is sort of my, I only discovered set diff somewhere, I think somewhere 15 years after using R, and it has been all the time there. And it is such a good, function. Basically, it takes two sets. Doesn't matter whether these are numbers or these are characters, names, or something like that. But what it said is sort of use the entire set of countries in the unfiltered data set, and then basically subtract, yes, difference, computed difference, subtract, take out all the countries that are in the Gapminder, in the filtered data set. And then you see that these are the countries that were in Gapminder, but that sort of were dropped out by the whole sort of pre-processing steps to make this a clean, clean data set, Gapminder, with full records, where every country had the same number of life expectancy numbers. Right, there were something like 45 countries essentially filtered out. Yes, 31 more than in Gapminder, meaning that we have now 29 countries more matched with polygons. Yeah, this is not just Russia, but this is 29 more countries that we have now matched by using unfiltered. But by using unfiltered, we can maybe not do the same thing as in the original script, because we now have incomplete records. We could, for instance, now take one of the years, filter for the year 2007, which I believe is the last year, and then select the life expectancy and create a plot, and we see a plot here. This is sort of the symbol plot that SF comes with. What we see here, for instance, is a country missing, which is South Sudan, which is a country, but in 2007 was not yet recognized as a country. Yeah? So here we have this thing that countries, are country definitions. Which country is a country is a matter of politics, and also changes over time, right? So, and this is in general the case with administrative regions. they change over time. Things change, and so the data collection changes over time. And if you do time series analysis over socioeconomic data, you have to take that into account and think of solving that. Yes, I know somebody who actually wrote a PhD thesis about this whole problem and had a hard time solving it. So I mentioned South Sudan. Let me see how far I am, because I wanted to go to the question and answers. Right.
There are two comments about the last topic. One is that one of the students used country code R package that matches such problematic country names.
Yeah.
And then another suggestion from Marcus is to use the ISO country codes provided in a separate data set in Gapminder.
Yeah, I think those are excellent suggestions to use. Country codes is, of course, much less susceptible to spelling issues. But then, of course, if you start, as I did, if you start with a data set that has just country name and that doesn't have country ISO code, what do? Right, so ISO codes are a great idea, but it should have been, that is something that I would have hoped that somebody else would have added ISO country code to this Gapminder data set. So if I have to add it, I'm still stuck with this problem of matching these names and matching Côte d'Ivoire to Ivory Coast. Yeah, so it's a good thing to use ISO codes wherever you can, but if somebody else didn't, you can't use them, right? You have to do the dirty work like I did here. Also, you don't think that ISO, because it says ISO, that it's not political, right? ISO is also political. ISO is the International Standardization Organization and follows member countries, yeah, which is a political process of coming to ISO country codes. So ISO, if you have an ISO country code, it might mean that you are a country for, in the eyes of particular groups of people, but not in the eyes of others. Right? So I don't know what the politics behind or how liberal they are. Will they give Hong Kong a country code or not, or Taiwan or whatever? No, it's be aware that even ISO labels are not sort of any guarantee for solving your actual problems. The country codes data frame from the Gapminder package does the matching. Okay, well, that's good. It's specific for country names used in Gapminder. Okay, so that is nice. Well, so then my problem has been solved. Yes, I'm happy that I'm just sort of, that is of course not surprising, because Gapminder is such a widely known data set that somebody did a better job than I did. I just wanted to illustrate you. For in case you end up having to do something like this with, with a less well-known data set. Also, I just wanted to point you out that, sorry about it. I wanted to point you out that looking at maps, you see big things like, oh, Russia is missing what's going on here. But of course, a lot of things you will actually not see, because you're looking at a world map, and most of the countries, or a large section of the countries, are actually totally invisible when looking at world maps. We do some math here. We can get basically the amount of pixels that we have on our plotting device with this command. Say that we have 1,000 by 1,000 pixels to plot things like this, which could be a reasonable approximation. And we could then, if we do this kind of plots, we basically have the entire equator sort of distributed over the width of the plot. So so we have a pixel size that essentially corresponds to 40 kilometers in real world, right? So we use the Earth radius in meters, and we divide by 1,000 pixels. Basically here we have the diameter, divide by 1,000 pixels would be 40 kilometer. So 9 by 9, 3 by 3 pixels then would be an area that is basically this value squared. And we can look at all the areas of all the countries and look at sort of the number of areas that are less than that have an area less than 9 pixels, and those there are 15 countries that match that criterion. And so we would really not see these countries at all when we plot them. Yeah. So this is not like, like the thing I did will catch the thing of the problem of missing countries or something like that. You really need to see which ones are missing, what's going on there. Another way of looking at what's going on is to look at the complete data set, which is the unfiltered data set, which has here geometries added, but I will not use the geometries, and to use the year, and it basically converted the year to a year index, which is essentially the starts a year at 1 and then increases to the number of years that we have. And I created a matrix here, which is basically a 2 by 2, which is a 2-dimensional table with the countries as row index and the years as column index. And then I put in all the life expectancies that I have using their row and column indexes as index to m. Yeah, so this is a way of filling an incomplete matrix with the numbers that you have. Yeah, because here we have the row and column index basically as argument. And if we then throw that into in the command image, we basically see the layout that we have, where I added the time, the years as the x-coordinate. I couldn't add the countries because there are like 140 of them, so it doesn't make much sense. But here you see the clear structure. Here you basically see the missing value pattern, so to speak.
Hello.
Yes, I can hear you. Okay, here we see the missing value pattern, essentially as a 2-dimensional space-time matrix where we have years, and here we have countries, and we see clearly that we have essentially life expectancy data for every 5 years. Yes, every year ending in 2 or 7, and that we have quite a few countries that have yearly data, but most of the countries only have 5 yearly data. And we also see that a number of countries are essentially missing for quite a while until they start delivering something in the 1990s or so. Yeah, so that is not very clear, but by the white, in principle, we have missing data, we have missing countries here, and here it starts. So this is one way of looking at the space-time layout as a 2-dimensional problem, like with time and with space as the other coordinate, and that is something that is relatively hard to digest from a table that comes this way, that essentially has 1,700 records, right? How are you going to look at whether these are, to which extent these unfiltered whether these unfiltered time series of Gapminder are complete or are incomplete. Right, so other things we can do then is with this unfiltered data set with geometries to select those years. That in any case makes sense, right? To go to the 5-yearly periods, because it's nonsense to look at yearly processes when nearly all when 90% of the countries doesn't have yearly data, but many of them have yearly data. And here we basically look at whether the modulo of year is equal to, meaning that the year ends in a 2 or a 7, modulo of 5 is 2, and we can then use geom SF on this data set, but add the facet wrap year, which basically means that for every year I get for every year it creates a facet and sort of organizes this in rows and columns in a certain way. And we see that here in the world maps. Of course, these are minuscule. They're very, very small. But we see that in any case, things like Russia appears in 1992 and not later. And yeah, that might have its reasons. Soviet Union and so on, whatever. Right, and here we see the same thing for the Gapminder dataset. Yeah, so this is the filtered dataset. This was the unfiltered dataset. This was the filtered dataset. Yeah, so I can plot that same amount. Good. So we are 5 before 12, and I also would very much like to keep my promise of having a break from 12 to 12:15. So maybe there are a few more questions that we can handle now before I briefly sort of go to this last part of raster data, raster image cubes, which I will do after the break. So is there anyone with questions now? Okay, then I'll just continue until 12. Yeah, so I'll keep to the schedule. Right, so raster data are sort of as a setup to discuss data cubes. Raster data are often used for continuous phenomena, right? So we have looked at life expectancy. Life expectancy is, of course, is an aggregate phenomena. You can't compute life expectancy from a single person, right? The thing is, I mean, you can estimate it, or so you can say the number for a single person, like or predict the times that somebody will live, but you can only get to these numbers if you have a large number of people over which you can compute these estimates, right? So it's an expectation, and it's computed over basically over the deaths related to the ages of people over a certain time frame and over a certain spatial area, right? Over a certain, it doesn't make sense to do it for a single person. It basically breaks the idea of an expectation, right? If you have an expectation, you can only expect something by looking at a larger number of people that are hopefully similar. Yeah, and you hope they are similar because you group them by the country and you say all these people in this country are similar, or you group them in some more clever way and do some more clever life expectancy modeling, which, for instance, insurance companies might do and say, I'm going to set your insurance rate depending on your habits or something like that. So they might do a more clever thing, but it's an aggregate quantity. There's a lot of quantities not aggregate that are essentially continuous in nature over space. Yeah, so think of elevation, think of temperature, think of air quality, or kind of physical properties, but also colors, right? So reflections of light, what we see in imagery, basically. And all these data are typically provided as raster data because they're either collected as raster data, or raster data is the most convenient way of providing them or creating them. Yeah, so they're collected. So if you take an image with your phone or with your camera, suppose you still have a camera, if it's a digital image, it's basically a raster, right? It's a CCD. It's a layout of sensors that are basically captured it, or it's maybe not a raster, but it's processed into a raster, which is some kind of a JPEG or something like that, which is a raster file. So if this JPEG has spatial coordinates to it, then it means it's georeferenced. It's spatial raster data. So raster data is usually regular, but it may come in other forms. And whenever it is regular, for instance, on the latitude longitude grid, and you would project it to something like Web Mercator or UTM or something like that, it becomes by itself, it becomes, you know, irregular. Yeah, if you would keep a grid cell, then you would go from regular, for instance, to curvilinear. And if you have curvilinear grid, the difficult thing is that you want to regrid it to something regular because it's too hard to handle, and that is called something called we call warping. Yeah, so moving from one, you know, from a rotated raster to something that is still regular. You need to resample things, and that is lossy. Yeah, you cannot resample without losing some of the original information. But that loss may not be a big problem, right? Think of JPEG, where most of your information is anyway thrown away because it's predictable and you want to just see a nice image without having all the data. It can be sort of without any problem. With raster, we also quite often have a time series, and time series is basically, you know, think of the easiest case when you take a video, right? A video is essentially the sequence of images that are time registered and that are taken at a certain frequency. Another case of time series is that of satellite imagery, where you have the satellite overpassing a certain area, right? We have now the top quality visible satellites is the Copernicus Sentinel-2 program, where we have an image every 5 days of this region, of the region where the summer school is being held. So that's Germany, and that depends on where you are on the Earth. If you are, you know, if you have other data like weather forecast data, you may have it for every 3 hours or every day or something like that. These data may be aggregated to whatever monthly data, because that's more convenient for particular cases. And here you have an example of a data set that comes from the package stars, where you see that we essentially have a raster data set, which has an X and a Y dimension, X and Y raster dimensions, where the reference system is missing regrettably for some reason, but where we have a time dimension, and the time dimension is basically our POSIX CT observations, which are printed here, so we can see there a sequence of dates. We have 12 dates, and they happen to be sort of regularly spaced over a year. You can see them here. This is basically every sort of last day of a month. We have precipitation values over a year. I think this was precipitation, was it? It's the first attribute. Yes, this is precipitation. Yeah, it says mm per m, but this is it's millimeter per month, right? So this m is actually a wrong indication of a unit. I now see this for the first time. But the good thing is that it comes with units, and this is temperature, which says capital C, but should of course be degrees Celsius. Yeah, so units are in this file, but are encoded in a wrong way. Where we have monthly values, and we essentially have a time sequence of raster imagery, which is not so far away from video imagery. Of course, in video you still have colors, you have RGB layers, so to speak, of your raster data. So I want to leave it here for this moment. It's 2 minutes past 12, so we will have a break until 12:15, and do come up with questions, because we should have time for questions, and that is most useful. And you know, my voice is getting problematic, so another 120 minutes of talking will be hard from my side. I'll see you in 15 minutes. Hi everyone, welcome back. I hope you can hear me.
Yep, that's perfect. We can hear you.
Good. So let me continue with the where we left off. So I have I'm a little bit ahead of schedule, which is, you know, which is okay. I had sort of I had anticipated a few more questions, or I had hoped for a little bit more discussion with either of you. Yeah, so keep that in mind. There is time for discussions. We are ahead of time, and you know we can, you know, I can, you know, I'm a teacher, so I'm basically, this is my job. I can talk as long as you want. But this is not what it's sort of what we are here for, what we came for together. So I'm here at Raster Time Series. That is a very common case, right? That you have time series of things. And that is also what we had basically in this case. We had time series of countries, right? So we have geometries and regular time series of them. Well, kind of regular, right? But in any case, if we go to the 5-year periods, they're pretty much regular. And if we then sort of throw out all the countries for which they are not regular, we end up with the Gapminder data set, which is entirely regular, which is this one, right? Every country has all the years that are selected here for which we have life expectancy. Yeah, so that gives you a layout basically, and that is what we, what I at least, or what many people sort of use for under the name sort of array data or data cubes. It means that we have sort of a multi-way layout, right? So here we have layout essentially of this table where we have years and we have countries, right? So that's a two-way layout. But we could have another sort of layer on top of that with different properties like life expectancy. We could have GDP and so on. So that would make it a cube. In this case, right, we have immediately a cube. We see basically, we see the slices, the time slices of the raster data. We see here basically as facets in our map, right? So if we sort of stack them, you know, on top of each other, we have basically X and Y as the two sort of spatial dimensions, and as the Z dimension, you know, the stack dimension, we have time. So we have a real data cube in that sense. If we have a color image also, we have in X and Y dimension, the two raster dimensions, and we have RGB, we have 3 layers. Yeah, so that makes it also a little, a small cube. If we looked at this data before, where were they? The data with multiple bands. Here we also have a data cube, right? We have X and Y, and we have 4 layers of these, 6 layers of these, right? So we also have a data cube where the third dimension is essentially the spectral dimension. Yeah, so this gives, so time and different properties or different attributes or spectral properties give basically addition give rise for another dimension. And this is what I sort of wanted to, what I try to address in this package STARS, which stands for spatial temporal arrays, raster and vector data cubes. I basically try to address raster data, but also time series of raster data, or arbitrary, more complicated array or cube forms, right? You could also have a time series of satellite images, which then has a time series. So it has the X and Y, the raster dimensions. It has a time series, but it also, in addition, has the spectral dimension, right? So that would be a 4-dimensional cube. So in addition to X and Y and time, we would also have a band, which is the different colors of each of the images collected at every individual time. So here we plot this data basically, where we do a little bit of a trick, because the trick is essentially that we add a function that plots on top of every slice, does a quick plot of the state boundary. So we can see that this is precipitation data for the continental, sort of for the land area of this area around North Carolina. And we use this country boundary essentially as a spatial reference. Yeah, so we don't plot, actually we don't plot the coordinates of the x dimension, the y dimension, because that would need a lot of space. But we basically put some kind of reference, some boundaries, administrative boundaries on top, so we can recognize it. Right? We can do the same thing with ggplot, and then ggplot tries to, plot these coordinates, which works here but doesn't work here because everything gets too tiny. And otherwise, what you see is that you have the same information, but every sort of submap is much smaller than it is here. So we have sort of, for some reason, we have much less space here to look at data than we have here. Another difference between the ggplot and the plot that we obtained here. Plot is basically a plot method for stars object. W is a stars object that we just created here on top. W. And another difference is the way that color breaks are being chosen, and stars does that by looking at the quantiles. So as I mentioned earlier, it basically does it makes sure that every color, if there are 10 colors, every color over the set of maps occupies like 10% of the region. So it kind of, in that sense, it explodes it explodes the amount of color you see. But on the other hand, you see here that this is a very high sort of precipitation area that is kind of has a single color because it is very rare, and here it is very prevalent. Here you have essentially equal color breaks. You have the range of data from 0 to 800, and you take a linear color range and cut it in equal pieces. Yeah, it looks like a continuous, but of course this is cut in pieces, where you see that essentially everything is close to very dark, below 200, and there's only one date where there's here, and here you see variability, of course, because this whole range is being used for this color range. Right, so we see very much differences in little details. This one, you could argue looks much nicer than this one, but this one you could argue has more information than this one, because every submap is 4 times as large for whatever reason, and the excesses are dropped, which are not really needed to understand this data. And the color range is different, although you could argue that this is useful, that we see variability in this particular region. Right, so we have then the issue of image data cubes and the issue of image collections, and there is that issue is not just one of that is not just one of data structure. Yeah, so I emphasize data structure, that we basically can see this type of information, either raster or vector data cubes. We can see them as arrays or as cubes. Yeah, with where basically the variability extends along certain dimensions, and such a cube is essentially being filled up. Yeah, in some way, and the way it's being filled up is essential information. And I pointed out, sort of starting from the motivating example was here, where I created such a matrix and filled it up with everything that is in Gapminder _unfiltered, so we can get an idea of where these data are, sort of where they lie in space and time, right? Where X is time and Y is basically country, which is then unlabeled. But nevertheless tells me, okay, where are these data? Oh yeah, it makes sense to drop everything but the 5-year sort of recurrent, sort of denser values. That makes sense. And then we have gaps, right? We have and the Gapminder wasn't there to mine, to mine the gaps of these data. It was there to mine the gaps in in the signal in these data, right? The question is whether it does a good job if these data have gaps in the sense of missing values, and what a pattern of missing values is, how to deal with it. And I argued that that basically looking at a data set in this way, looking at it as a table or doing a group by is not easily revealing that certain areas are missing. So if somebody cooked it up and said this data set is complete, all the time series have equal length and have no missing values, then you're happy, yeah, except that you have to scrutinize on what happened before that and why you're missing out 50 countries, 55 countries. But otherwise, you know, if you don't accept that or have to start from scratch, then you really need to look into that and think about how to deal with that, what are complete records, how do I deselect them, what happens when I deselect 55 countries, what happens to my story, right? What sort of comes out, to what in what sense are my sort of findings still generalizable, or how do I describe them when I sort of when my data cleaning operation basically dropped 55 countries. I said 55, but I think it was 35 or so, right? 42, there were 142 countries in Gapminder, 177 in Natural Earth. So this is one aspect of image data cubes is that of data structure, that these data, when you want to use them, have a relatively complex structure that where it is often helpful that if they are distributed over dimensions, that you also sort of analyze them in that sense by dimensions, because the typical thing, the typical thing you don't want to do is sort of throwing away all your information before you analyze them, right? You would like to analyze all the data that's relevant for your problem. And if you start off with saying, okay, I have a time series of something, but I have no clue how to deal with spatial time series, so I select a single slice and continue, then you're basically, this is the worst case situation, right? Where you sort of drop an entire dimension entirely simply because you have no clue what to do. Another challenge is the size of data sets, and that is a more tricky one. If you think of if you think about areas like this, or areas covering Germany, or areas covering Europe, or even global areas, and you think about using satellite imagery, then the good thing is then that a lot of high quality satellite imagery for all kind of variables, spectral information, Sentinel-2, radar information, Sentinel-1, air quality information, Sentinel-5P, sea surface temperature, I think Sentinel-3 or something like that, and there are all kind of US programs as well. So these data sets are in principle for free. The thing is that when you want to work with them, that these data sets are pretty large, right? And that if you want to analyze data, as I said here, analyze data set over a somewhat larger region, even at lower resolution, or if you want to look for a limited area, but over a larger time span, and want to sort of cover the whole time variability of the data sets obtained, because you want to do sort of look at dynamics in agricultural crops or something like that, then you end up in a situation that if you would like to do that download, that you basically have to download a lot of information. And downloading a lot of information depends on what a lot means, but it's quite easily, it is kind of obstructively large to really work with that. Yeah, so if you then want to work with these data, then there is no sort of real other options these days than to work with cloud platforms that serve these data and that allow you to work with these data. Yeah, and we are in the process of creating such cloud platforms that sort of work with open source software stacks. Right now, if you want to do something like that, then the only sort of realistic option, embarrassingly, is probably that of Google Earth Engine, right? Which is a which is a fantastic product, but which is also a product that is built on closed source software and on end-user license agreements that might not sort of correspond to the requirements of your work or of your study or of your scientific ethics that you try to maintain. So hopefully there will, things will improve in the near future, but that is hard to look in the stars. Yeah, and that is a little bit the same proposition as you have with ArcGIS. You try to do proper data science, but you will simply find out that when you want to do everything with Python or with R, then it might be more work. It might be more difficult to do than taking an off-the-shelf commercial product that is seemingly much easier to deal with. One thing I wanted to that I can look at with you sort of before I go into the last section on models is that of how to deal with larger data sets in R, right? And there is a chapter on that, which I didn't repeat here. There's a chapter on spatial data science here on working with larger data sets. As you see, there's a chapter on data cubes, the concepts of them. There's a chapter on SF and stars, and there's a chapter on large data sets and how to deal with them, either with SF or with stars. And the issue is that when you work with R, then R is a software environment for analyzing statistical data and visualizing them. That is very sort of powerful and flexible, but it basically works with the concept of data being in memory. Yes, this is the basic concept. This is essentially comes from the idea that you work with observations, and that observations are, that observation takes some time to do well, for instance, doing an experiment, collecting observations and so on. And that you then sort of analyze these data. You can put these data in memory because they're not, they don't explode your memory for some reason. Now, this whole idea of observation, yes, has changed a little bit in the sense that we now have these satellites sort of circling the Earth, bringing down a couple of terabytes per day. Yeah, so that's petabytes per year. So we have data sets that are really so large that they kind of, even, you can keep a couple of scenes, a couple of images of these data on your hard drive, but you can't even sort of get these data by downloading. It's so much. Other areas where we have these large data sets are that of bioinformatics, where people use these next generation sequences where you put in some dirt and you immediately have gigabytes on gene sequences and so on, right? So genetic data is another reason why we have very large data sets, or let's say relatively trivial observation leads to incredibly large data sets. So that reality of statistical data being of a relative comprehensive size is kind of, is no longer so much sort of something of today, right? And then the question is like what happens and how are you gonna deal with that? And this chapter sort of introduces a number of strategies to dealing with that, depending on sort of your situation, right? Where your data are. Sort of, there is a couple of situations I could think of. Either your data is too large to fit in your working memory, and then it basically means it's on your hard drive, but you can't load it all because your memory sort of is too full. What to do then? It's also another next stage is that it's too hard to fit on your local, too large to fit in your local hard drive. Or it's even too large to download at all. If we think of downloading a petabyte, it's something you think is doable, but it's probably, you know, it is because you tend to download relatively small portions, and you think, hey, but my Netflix also, you know, is big data and so on, and I have a complete DVD essentially downloaded in like 2 hours or something like that. But it's not going to work if you download data sets that are really sort of petabyte size. Then waiting times are infinite, yeah, because if you do a very large download, you'll be essentially being penalized compared to everyone else. So there is a certain set of size of data sets that is unrealistic, that even if you are running a lab with file servers and everything, it's unrealistic that you're being able to getting it downloaded. So you need to do other things. So reading from disk is one thing that we already did, right? That we already did. What you can do with the ST read from reading SF is that you basically give a filter, that you give a polygon, for instance, a polygon here with a simple bounding box, and say, if you read it, filter it to this bounding box. So if you have a massive polygon data set, but you only need a small section of that, you're not going to read it in its entirely, try to hold it in memory, and then do the selection in memory. No, you basically, in the read activity, you say, discard everything that is not inside this bounding. So you're only reading the things in memory that fall inside this bounding box. So this is a massive sort of lifesaver if you are having a geo package or a GeoJSON or a shapefile that is many gigabytes of size, and you're only interested in a small region of this. Yeah? Of course, you might be interested in the entire data set. And then you need to think, how do I go through that? You know, piece by piece or something like that. There's other things you can also do, sort of SQL type queries. So you could, in principle, if your data set has an ID or something like that, that goes from 1 to n, you could go through each of the polygons, right? And sort of write a loop, and every time sort of read a chunk, analyze a chunk, process it, write output, go to the next chunk. So write your own sort of looping device to go through a massive data set by using SQL statements like this. These are ways to constrain your your data sizes. Another option that is probably more robust and also even more scalable than the previous one, it says, well, I don't have all my data sets in I don't have all my data sets in as files on my hard drive, but I have them as tables in my database. Yeah, and then what comes to help is essentially this database interface that dbplyr has. Yeah, so dplyr is an interface to tables, right? Data frames or tables, and has all kind of select and filter statements on it. If you're the idea here is that if your table is not, let's say, a table that's realized as a data frame in memory, but it's basically a pointer to a table that is somewhere in the database, you can use dbplyr and tell it where this table is, and do the same commands as you would do as if it were in memory, and basically carry those activities out in the database. Now, databases have been written especially for this purpose, that they do their thing independent of how large your data set is. Yeah, so they will take their time, of course, but they will finish, right? They will do it. And it includes doing things with spatial predicates if the data set has spatial capacities. Yeah? If it's a spatial database like a PostGIS database or something like that, you can do these things as well. Yeah, so that is a scalable way of doing things that is probably more feasible. And here are sort of a couple of examples doing this. Other things, when things come to reading, is basically reading things from web services, and this is a very common thing, that your data sets are not files on your hard drive, but they're essentially basically somewhere on the web, and are being sort of proxy or interfaced through some kind of protocol. And one way is, for instance, the OpenStreetMap database, which is sort of a very large database that everyone probably knows from it, it's a little bit like you know, like a Google Maps database with administrative boundaries and all kind of streets and routes and paths and buildings and all kind of things that is sort of collected, put together, compiled from all kind of public data sets, augmented with all kind of crowdsourced data. Yeah? So you can become a provider of or improve this OpenStreetMap data set. And that has an interface where you can basically either download files or do direct queries with a certain region and say, give me all the features that intersect with this small region, and not having to download the full data set, but doing a direct query. Like here is a query of doing something that interfaces with this dotted area. And then plotted only in this region, right? So the features, the street features are of course much larger, but I just plotted them, I constrained the plot to this region. And for raster data, there is this thing, the thing called like cloud optimized GeoTIFF, which is a relatively new technology where we can have massive grids of very large raster files that we could theoretically download. But if we need a certain subregion of it, of that raster data set, because our sort of study area is much smaller, then we can directly sort of access that without much effort, but with a very sort of lean query and with a very responsive protocol that gives you immediately that sub raster, so to speak. And that's a technology that is sort of revolutionizing this whole imagery use of massive imagery in the cloud. So in such a sense that it really even becomes responsive in browsers. And so if you do a tile surface, things like that. Another way of dealing with data is basically that with raster packages like stars, and well, stars is more generic for data cubes, but includes raster data, but also packages like raster and terra do. And that is essentially that if you have a large data set, you're not going to read the entire data set in memory, but you're going to read essentially a proxy. So you read the metadata, you read where it is and what the file size is and so on. And you're not going to read any pixels before you need them. Yeah. So here's an example that uses this stars data package, which is a package that is not on cron because it is 1 gigabyte in size. So it takes a while to download and install. And here is a Sentinel-2 tile that is there, sort of part of the data package that you can see that has a pretty large, almost a gigabyte in size, and you can sort of load it here, and it loads in a very short time. But what it does is basically it gives you the table of metadata information, right? Which again says this is UTM data. It's an 11,000 by 11,000 raster with 4 bands. Yeah, so it's a very large data. It doesn't load any of the data. It just holds a pointer essentially to the file. Like, okay, this is where the data are. Whenever you need it, then I'm going to do reads. But if I essentially ask the size of the object, you see that it's a tiny object. It's essentially the size of this metadata table. And then what it does is all kind of, basically collecting all kind of subsequent operations on it. So if I say, okay, multiply this whole image by 2, then it doesn't do it. It says just, okay, when pixels are being read, I still have to multiply them by 2 before I do something. And this is interesting sort of approach. And also when it says plot, when I say plot, then it's going to downsample. It says, okay, I need a plot. Well, I have 1,000 by 1,000 pixels, and I need 4 tiles, 4 of these facets. So how large would a pixel be then? Okay, pixel would be like 200 meter or something like that. So how many pixels do I have to read then? That is, well, 1 every 20 row or something. So it's going to downsample with a ratio of 19. So it's going to take every 19th column of this raster and every 19th row of this raster, because those are the pixels that are visible. You know, it could also read everything and then plot everything, and it would take 10 minutes, and it would basically discard 99% of the information because there are not enough pixels to basically plot. You know, on my screen there are not enough pixels to plot all these pixels to. So it's doing this downsampling, which is basically a speed up and doesn't cost you anything in the sense that you see less than you would otherwise see. And that is, you know, that is one way of handling that. And packages Terra and Raster do it in a slightly different way than stars, but it's one way of sort of making it doable and somewhat responsive to work with massive imagery, and sort of not, you know, avoiding to loading more information in memory than you have, or than what is needed. If you wanted to sort of save this map, the P2, which is basically P multiplied by 2, so then that means you write it to disk, to another external file representation. Then it would go through the entire image, but do this chunk by chunk. So read a part of the raster, multiply by 2, write it, you know, discard, next part, multiply by 2, write it, and so on. So it basically does this looping, this caching or looping, whatever you want to call it, on these data sets. So that is an approach that you can work with very large data cubes. There are other aspects of imagery data sets, and that relates to the aspect of let's see where I am. The aspect of image collections, and that is that if I have imagery that are not if I have imagery that are not lined up very well, yes, then this is another problem, right? If I have, let's say, if I have regular rasters distributed over the Earth, but they are all in their own UTM zone. Yes, that means here they are in UTM zone 32 north, but then, you know, 500 kilometer east, they are in zone 33, 33, 35, and so on, right? So they have different coordinate reference systems. That means that I have imagery. Another issue is when I have overlapping imagery, right? All these satellites kind of, they're not, you know, they're not nicely cutting the Earth in parts. They just pass over and pass over and pass over. So we have all these overlapping pieces and so on. So in any situation, we don't have sort of a nicely laid out regular data cube, but what we typically have is what we call an image collection, and it is just a collection of images that in the end cover the Earth, but with, you know, with different times of overpass and with different coverages and certain overlap, and not at all matching nicely matching up. And so an activity that you need to do then is basically go from that image collection and create a data cube and say how you want to sort of combine these different things that don't match spatially and that are sort of have different overpass times that don't match nicely up, and bring them together. And that is what we basically call image cubing. And that is something that is hard work, and I mean, it's computationally a lot of work, and that you need to think about your parameters and so on. So that is something that happens in cloud platforms, or that you can do whenever you have downloaded tiles and need to sort of combine them into a so-called mosaic, yeah, which then hopefully is an image data cube. So are there any questions related to that section on data cubes and imagery raster data?
No questions for now, I think.
Is there anyone of you who has ever worked with satellite imagery or raster data or models, sort of model results, climate data or weather data or things like that? Yeah, I can understand. You know, you had a long week or 2 weeks of data science courses and all kind of topics. I can understand if you're all worn out. Thanks, Marcus. A bit with raster data only for a workshop. Yeah, it is similar to here, right? So the big disadvantages of these things. Like this workshop here is that I prepare my stuff and in a way that you can run it and you click run and it runs if you're lucky, and it looks very easy, right? And then comes the hard part, which is when you are confronted with questions and somebody else tells you, well, here's try to make some useful assessments about climate assessments over this region or something like that. I see. Yes, and of course, vector data is more common in social sciences. That is right, but of course, some questions are also associated to aspects that don't come as vector data, right? Bitan wrote, I have previously used magics in Python packages while working on European weather data. I see. So that is also on raster data, right? Magics. I don't know the magics package, but all right. So here we have Nguyen, who says, I'm trying to work with quintennial population data using gridded population of the world and ran an example of temporal interpolation. Right, so that is definitely socio-economic data that it comes as gridded data, right? So these are relatively modern attempts of creating global rasters of population or population density, whatever, and that, as I said, that makes sense. That makes sense to the extent that what I said was that when you look at population data, you do it by administrative regions, but the administrative regions were not there to tell you about boundaries in population densities, right? So if you want to look at population density as a process, you would ideally have a uniform spatial unit, right? And that could be a raster, right? That could be a raster. Of course, there's the challenge that if you do a regular raster for the whole Earth, then your rasters will have a size of a certain amount of degrees, like say a quarter degree by quarter degree, right? Which would be like 25 kilometer, or then maybe a tenth of a degree, right? Which would be 10 kilometer on the equator, right? But if you go north, a tenth of a degree by a tenth of a degree is only half of that. And if you come close to the pole, then, well, luckily not so many people live there, but then the size of that raster cell is essentially zero, right? So there is a challenge of finding good rasters that basically have somewhat equal area cells. Regular rasters won't do it. So one way out of that is, for instance, to use hexagonal tessellations, which have a much more regular, which you can do globally with much more similar sizes of individual hexagons. You cannot cut up a circle, a sphere in equal parts, only in a very few ways. But there are tessellations that do this. So thanks to Nguyen, recently trying to understand how and why we need temporal interpolations. So you used the gridded population of the world and ran example of temporal interpolations. So that you have, like for the gridded population of the world, various time instances of that same sort of raster data set. Yes. So so does anyone know how these gridded population data sets, how they are created? The answer is a URL. Thank you. All right, so it models. Right, and the essential input, obviously, as I said, are census tables corresponding, population census tables and corresponding geographic boundaries, right? So we have counts, population counts by administrative regions. Yes, depending on probably, you know, for certain areas, you will only have country totals. For other areas, the country might do more precise census or sampling processes and provide it for smaller areas. But from there, you need to go to raster values, as you see here, right? And you need to have additional information to redistribute it, basically. And what they do, they call it disaggregation. I called it downscaling, but disaggregation is essentially the same thing. Yeah, here they say this 30 arcsecond, approximately 1 kilometer. I think they mean 1 square kilometer at the equator. And once you provide population density, it's okay that these grid cells are of varying size. If you create population amounts, then you have a problem when this. You need to take into account that the grids are of different size. Okay, so yeah, Nguyen said it can be found here. Sorry, I did not make myself clearer. I'm only trying to understand how temporal interpolation works in theory, since the data is available in a 5-year interval. And I understand you need it in a 1-year interval or so. Yes. Yeah, so that is another case of downscaling, right? You have 5-year data and you want to have 1-year data. So that involves modeling. It says here, population input data are collected at the most detailed spatial resolution available from the results of the 2010 round of population housing censuses, which occurred between 2005 and 14. And then the input data are extrapolated to produce estimates for 2005, 10, 15, and 20. Well, you know, that is, if you have, okay, this occurred between, so they already did some kind of interpolation, extrapolation. In any case, they had sort of something that occurred between 5 and 14, and then went to do, you know, to create these set of products. I'm actually quite surprised that they suggest that they have a uniform data collection process, which is global and says something like this. Yeah, because every country does this differently. So homogenizing these things is really, you know, I mean, with a couple of assumptions and a couple of input data, you can, you know, you can create anything. But the question is always like, how realistic are the assumptions that you're making, and how valuable, how meaningful is the result that you end up with? So don't take that as criticism. It is just that these things are very hard to do. Right. So you would need to go, Nguyen, you would have to look into the paper. I hope there is a paper that underlies this data set. I assume there is, where they detail and how they go from what kind of information they have here and how from that they created these sort of 5-yearly data over a span that is quite a bit broader than, you know, the span they have is 10 years and they now go to a span of 20 years. So that's why they use the word extrapolation, I think. But you could, you know, anyway, there's modeling going on there. And the simplest way, obviously, for temporal interpolation is sort of straight line interpolation, piecewise straight lines, right? So so assuming that nothing, you know, nothing drastic is happening between these years, it's a continuous process, right? Population increase or decrease, and you don't anyway. If these if these values are already extrapolations, essentially model results, then assuming sort of regularity and that the process is continuous could lead you to a very simple and interpolator that might simply do the job. If you have, let's say, if you have the data that they had, right, that would be proper science. If they would share the entire data set, that was the input for them. And you have the procedure that they used to create these 5 years, right? Then you could do exactly the same thing, but instead of these 5 years, create a yearly data set using the same model. Yes, that would be the ideal situation. That would be the proper, reproducible, you know, scientific approach that everyone should do. And that would lead to a lot of good stuff. The problem is that in practice, you know, you rarely find that because they are essentially sitting on it or find it too complicated and just distribute this result and images and that's it. Yeah. So, but you know, you might contact the authors and say, hey, I need yearly estimates instead of these 5-yearly, and could you give me the data and the basic inputs so that I can run the model and get the same sort of model predictions on a yearly basis? They should do that. NASA people should do that. They are very much into open science. NASA. Good. Yeah, so that is an interesting case of a raster data set of socioeconomic data, right? Where they and the reason to do this in this way is obviously that you don't want to sort of get trapped in this modifiable areal unit problem. of your analysis depending on the size of your spatial units. Having said that, of course, you need a model to go from population counts as they're counted based on administrative units to a raster, a continuous surface representation. Or it's not a surface, it basically counts densities within raster cells maybe, but even on sort of in a more uniform spatial unit form, like a regular grid. And you need a model for that. Yeah, so the model for that is essentially that of what they call asymmetric mapping. That is that you have a number and you want to redistribute it, and you have additional variables that are informative. Where you would, for instance, use for each raster cell the amount of urban area or something like that, right? So if a raster cell is entirely urban area, you can assume it has much higher population density than a raster cell that's entire agricultural. So we have this land use or land cover products on a much finer scale than administrative regions, and we can use that as, you know, those are usually used as the first, you know, as a first guess to redistribute population within areas for which you only have totals. Good, thanks for the question. So keep them coming up, right? Can you tell us more project research examples using raster data to understand social problems, phenomena? Well, think. So right. So as I said, a lot of information is collected on administrative regions, and we have directly the problem of the difference in sizes, right? So we have, even if you look at Europe, we have the NUTS1 regions, right? And then we have like I think NUTS0 are the countries, NUTS1 are sort of the first level districts. In Germany, NUTS1 are Bundesländer, yeah, I think federal districts or something called in English. In the Netherlands, we have provinces. Well, the Netherlands is the same size as one NUTS1 level area in Germany, because, you know, Germany has like 16 of them, but a couple of them very small one, and is a large country. And the Netherlands is a very small country, which is the same size of North Rhine-Westphalia, essentially. So we can, you know, we can choose a level of something, but it doesn't mean that we choose a particular size. So anything of these NUTS levels, administrative regions sort of levels, doesn't mean anything in terms of the sizes and whether they are, you know, useful for a particular phenomenon. So anything else sort of picking, you know, making size the preferred sort of unit, sort of picking units of a particular size, means that, for instance, we do this global population grid, we go to particular raster sizes. As I said, rasters, regular rasters, is not a very good idea for global data because of latitude, longitude rasters having such a different size when you go north or south, becoming much smaller. But the ideal would be hexagons. But anyway, you know, getting a more uniform size is always a better idea in that sense. So so redistributing all kind of information to finer level sort of semi-continuous surfaces is not a bad idea, as long as you can do it properly. And for population density, you can do it properly if you have information like land cover, where you put more things in, you put more emphasis in areas that are urban. Then you put more population in areas that are more urban than in areas that are agricultural. Other aspects are, for instance, when you are looking at movement of people, right? So if you're going to simulate some kind of movement process, you could also do that. You can do it in different ways. If the movement is all through road networks, you could use a road network for that. But in general, if you could do movement, you could also sort of simulate people. If you do if you move around pedestrians, for instance, right? They can move freely and go off the road and something like that. Then you could use a raster representation and say, I'm going to do some kind of an agent-based simulation where basically a person is in a certain grid cell and can move to another grid cell, but only with a certain speed and things like that. So there, a continuous space representation makes sense. And since we cannot deal very well with continuous space, we typically then rasterize it in some way. So we discretize the space, and that typically leads to raster structures. So agent-based simulation, geosimulation models are another example of that. And otherwise, so yeah, that was it. You're welcome. So we go then to the last section of my summer school contribution on GeoData and spatial data, which is about models, right? And so far, we touched a little bit about models. Sort of the Gapminder data was purely explorative and descriptive. We touched a little bit about modeling when we talked about interpolating temporal phenomena, or when I mentioned sort of how these gridded population of the Earth are created. I can't get here the gridded population of the world, how these are created. That involves modeling. There's no way around. There's no measuring. You can't measure population on a kilometer grid. So you need amounts for larger areas and redistribute them using additional information in the model. The goal of data analysis, as I said, is often beyond descriptive statistics and exploratory graphs, but may involve, for instance, inference or estimation of effects, estimation of relationship between variables, or estimation of means, or properties of the process that most likely generated these data. These are all estimation and inference, or even model identification issues, right? So is my variable, does my variable have a trend in time or a trend in space, or are two variables related? Is my population density related to land cover classes? Yes, obviously, but you may want to estimate it, right? You need the numbers, you need the different numbers, estimate the different numbers, the population density on land cover class, urban and on land cover class, agricultural, in order to be able to do this redistribution. And there are errors, you have sampling errors with both, and then you get uncertainties in the redistribution and so on. So you can do this with proper statistical modeling. Other things are prediction of unobserved variables. Yeah, you could argue that disaggregation or downscaling is a prediction problem. Yeah, we had the missing values in Gapminder. They were basically all removed. Yeah, but we could also predict them. We could do an imputation approach to replace the missing values with most likely, life expectancies, and then using the impute datasets to do a more comprehensive analysis that includes also countries that have incomplete time series. And we can also predict properties that were not observed directly or fully observed. For instance, predicting land cover from satellite imagery. Satellite imagery are colors, right? So we see colors, and we use greenness or NDVIs to basically indicate the amount of vegetation, and from that we derive whether something is forest or agricultural, and we look at the time series, or whether it's urban and so on. So those are classical classification problems, or prediction problems, right? And problems special to spatial data are often feed back into the sampling process and the goals. And one question there that is often overlooked is whether analysis can proceed in a design-based way, right? If you have some kind of, the observations you have are collected by some kind of random sampling strategy or not, right? And if this is not the case, you cannot do a design-based analysis. If it is, and you know the sampling process, you know the inclusion probabilities of your observations, then you can do a design-based analysis. And if the random sampling was done, if there is sufficient independence, you can use the proper equations to do a design-based approach. And that means that you can abandon the problem of spatial correlation, right? That near observations are similar to other near observations because there's randomness in the sampling process. Quite often this is not the case, and quite often you have to basically proceed with a model-based approach, where you essentially consider the observed variable as a random process, as a random variable. And this random variable then typically is spatially correlated, and you would have to address that spatial correlation in your analysis. And this is often happening, of course, not happening, right? So people just do some kind of whatever regression, logistic regression model, or some kind of modeling approach, or some kind of machine learning process like a random forest because it is so good. And they throw that on the data and they ignore everything that's basically potentially spatially correlated, and then end up with predictions. And the whole problem is then that for these predictions, you have very little clue how meaningful they are and what their prediction errors are, because you essentially started off with assuming that, or using a method that was designed for IID data, for independent, identically distributed data, and they're not. If you have a spatial process, then your data are not independently, identically distributed. Yes, they are, rule one, they're not independent, no, they're spatially dependent. Right, and then you go back and you say, okay, spatially dependent, I would like to do random forest, and you're basically stuck because there is no random forests for dependent data. Yes, or at least I haven't run into one. So that doesn't mean that you have to throw away the random forest altogether, but that it's just very difficult to do this in a proper way and to really say something about prediction errors, which is, any prediction without a prediction error is basically the only thing you can say that it's wrong. You just have no clue how wrong it is. Yeah, this is the whole sort of clue behind using proper statistical methods, is that you can say it's a prediction, it's wrong, and I can tell how wrong it is. This is kind of the standard error of my prediction, and it's a good measure because I used a proper model. I'm going to briefly talk about three approaches of modeling. One is point patterns, one is on geostatistical data, one is on lattice data. And they are basically the classical sort of three chapters that you would find in a book on spatial statistics. And they are useful to know, even although I know that the third one, lattice data, data associated with polygons, is the dominant one in socio-economic analysis. I will also briefly talk about the other three because it's useful to have an idea about types of data, sort of statistical process, and whether something is a point pattern, geostatistical data, or lattice data. As I said, lattice data is data associated with areas, typically with polygons, but they could also be associated with raster cells when they are areas. Point patterns and geostatistical data both start from point observations. Here we have a data set that I read from here. So here is a website. Oh, why doesn't this work? So here's a website, which is something Esri open data. So it's an ArcGIS provided website, which I don't care too much about, but it has a download button somewhere that I found. Here, this is the download button. So you can download this thing, right? And what I did is download it as a GeoJSON, not for whatever reason, but I don't like shapefiles. So GeoJSON is, in any case, it's one single file, which is useful. So I downloaded it and then I saved it. It got saved here. So this is how I read it. And you can read it basically. Oh, this is how I read it. I think you can even read it using the direct URL, but I don't think that this gives you a URL. This gives you just a button that downloads the file instead of giving you a direct URL that would fetch the file, which then you could put in this place if you had the URL. It's not. Yeah, so these are windkraftanlagen. So they are wind turbines, distributed over Germany. And I combined them with the natural earth data set. And here I read the natural earth data set using a scale of 50. Yeah, so that's a little bit more detailed than the default scale? Yeah, good question, Beaton. What is the advantage of using a GeoJSON over other formats? Yeah, this is the question, right? About data formats. So, does anyone have an idea what an advantage of a GeoJSON over other formats could be, or maybe a disadvantage? Everyone is typing now. Aren't GeoJSON lighter than shapefiles? Lighter, I assume, is sort of smaller in size, right? Yeah, we would have to look at that, whether they are lighter. Shapefiles, the thing is that shapefiles is, we can do it. Let's see what happens if we do shapefile. We can also do CSV, and we can do shapefile. Onshore, they are all called onshore. We're now in let's see how they look like. So here we have the CSV. Yes. Let's see if we can open it and see how this looks like. Yeah, it doesn't look so bad, right? You see here, because this is point data, right? This works. So we have the coordinates, the X and the Y, as the first two columns. So we could as well have used that, just use the CSV. Okay, Bernd, I will come to your question a little bit later. So CSV would work, right? It is the comma separated values, I think. Yeah. So the first line is the variable names. We could use this. Oops. Now I have the different. Sorry. I have to add the wrong thing in my mouse buffer. Yeah. So we have R, which is X and Y, right? So from this we could easily do library as F and then convert it as F. R with coordinates is X and Y. And we have a CRS, which is of course ungiven, but let's assume it is CRS is EPSG 4326, right? WGS 84, which is most likely. And then we have the wind turbines. Oh, it gives an error message. Yeah. So there are missing coordinates. Yeah. So let's just clean the whole data set. Whenever there's a missing value, it will not clean everything, but it works. Yeah. So we could plot, for instance, the way the wind turbines with variable Gesamtleistung, yeah, which is the power that it generates, which is now looking very unnice with an unnice color scale, because it's considered as a yeah, I remember that. It's considered as a character variable, because this is a German data set. I get my data in a German format, which means decimal commas. Yeah, you might have found on your forms and so on decimal, or on your the interface to your bank account. You always have to give numbers with decimal commas. Otherwise, it's not German. So you would have to replace the commas with points and then convert into numeric. We'll do that in the example. That is one example. The other was this one, and as you see, this is the shapefile is downloaded as a zip file. Yeah, so I can look at what it has. And when you see that the zip file contains 5 individual files. Yeah? So the fun thing about a shapefile is that it has always 4 or 5 files. Where we have the DBF, which is basically, and DBF is a very old-fashioned way of, it was a software actually called DBase, yeah, the way we now would use something like a database like Access or something like that. So this is a very old-fashioned file format for attributes. And the fun thing about this database, DBF format, is that attribute names can only have, I think, 10 characters or something like that, right? So so probably if I look at this field, projectierer betreiber, it might not be in there. So let's unzip this thing and then read it. Windkraft, then have to give the shape, the dot shape, and then it will read it. And you see that that these original field names, like this one, are now shortened, right? And also Gesamtleistung megawatt. Yeah, you see here Gesamtleist. Yes, they are all shortened to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 characters. So field names can only have 10 characters. Well, that is something that is so much out of, that is so much unnecessary that that is sufficient reason to completely abandon shapefiles. Many other reasons are that shapefiles are still a proprietary format of ArcGIS or of the Esri company. It's not a published open standard. So it has been reverse engineered, otherwise we couldn't read it with R. But that doesn't mean that it's a good idea. Yes, there are actually many reasons why shapefiles are no longer a good idea. GeoJSON, I don't know if they're lighter. I don't. We look at here. We see that the GeoJSON is the largest from all, but then the shapefile is zipped. Yeah, okay. Yeah, so the shapefile is 3 megabytes. Yeah, so the GeoJSON is actually lighter. It's 2.5 megabytes. It's lighter than the shapefile, but then the CSV is lighter than the GeoJSON. Yeah, so none of them are big data sets, really, in the sense of problematic or something like that. GeoJSON has the advantage that it's comprehensive. The CSV doesn't tell you what your coordinates are. So to import it in a spatial data set, you can do it because there's a field X and Y, and because these are point data. So X and latitude, longitude are just columns, X and Y, and that's fine. But it doesn't tell which columns they are. So you have to figure that out or guess. It doesn't tell you what a coordinate reference system is. Yeah? GeoJSON does all of that, right? So as shapefile does, but shapefile has the big disadvantage of cutting all these variable names, and by that basically dropping the units of the Leistung, right? We had a Gesamtleistung in megawatts, yeah, which is basically dropped. I mean, it's a bad unit. It's encoded in the variable name. It's not a good idea, but nevertheless, it's information. Right? It's lost in the shapefile. So shapefile is something from the past that anyone who tries to give you a shapefile, you should actually ask and say, hey, where are you living, right? This is we passed 2020, and this is like, this is from the previous decade, from the previous. Shapefiles are not from today. A good alternative. One disadvantage about GeoJSON is that it is a text format. Yes, it is as JSON is. Of course, there are ways of putting binary stuff in JSON, but that is not a reason why you use JSON. So it has, advantages and may have challenges. I don't know how easy or how difficult for some it will be that there are names in this that have particular characters that have a particular encoding, right? So this might come out good or bad depending on what your machine assumes for encoding of text files. So that is one issue. Another issue of encoding numbers as text is that this is not the way they're internally represented. They're internally represented as 8-byte doubles, and that is basically a binary thing, right? So if you have a representation and write it out as text, how many digits should you use to sort of, to make sure that when it's read back that you get the same number? This is always a challenge. Maybe this is enough. Maybe you get a slight difference by conversion to text and from text to binary, right? Of course, it's not significant, but the two numbers might not be identical, right? So the path going to text, human readable text, and then reading it back into binary might give you lots of information. Might mean that you are going to look at equality later on, and you find no, it's not equal to this thing. It's another point. And then it turns out to be 1 millimeter difference. But yeah, it's another point because it was written to text and back. So I'm not a fan of sort of doing this, but it's, a lot of people like JSON, the JavaScript people essentially, yeah, which is a good reason, and it's surprisingly successful and so on. It also comes with a coordinate reference system, as you can see here, which is the CRS-84, which is essentially WGS-84, but explicit about that coordinates are longitude, latitude in that order, and not in the reverse order. If this were WGS-84, it should have been officially in the reverse order. At least this is exit order hell that I don't want to discuss. A good alternative that I actually propose and also use in my slides is that of the GeoPackage. And GeoPackage is essentially, for instance, here you see this file is read as GeoPackage, which is a file in a database. It's an SQLite 3 that is a relational database in a file format, and it has a specified schema where it's clear, where it states where the geometries are for every table, where the table with the coordinate reference system is, what the coordinate reference system of geometries is. So that is, in that sense, and it's binary, yes, in addition. So I think that is a very good alternative, modern alternative to sort of exchange spatial information in such a way that everyone can read it. Yeah, that Quantum JS can read it, PostJS can read it, everyone can read GeoPackages. And you don't want to, you're doing data science. If you are exporting things as shapefile, this you should never, never, ever, ever do. You're cutting all your file names to 10 characters. I was thinking about, no, there might be upper cases in it, but you're cutting all your file names to 10 characters, which is absolute nonsense. Right. We have the question, before we go further with models, we have the questions from Bernd, two not directly related questions, which may be answered whenever they fit. Do you have any advice regarding travel distances between places, especially between European towns? There are problems like travel times differ by land and water. How is this calculated? Are there any data sources you could recommend? Yeah, I have. So Bernd, I have some advice here. One is that there are public services that give you travel times through the OpenStreetMap data, or at least that give you travel distances. Yeah, travel times is of course depending on the speed you have. So if you go through a road network, it depends on how fast you are allowed to drive and how fast you can drive, right? So travel times is in that sense not independent of the question in the sense of which means do you have to travel. But shortest paths through road networks are definitely feasible, and I think can be gotten from the Overpass API, which is an API to the OpenStreetMap road network. Travel times over water, I don't know. Yes, here you're thinking about traveling by ship, right? Which is a very different activity. There are in principle a number of packages dealing with network data where you have spatial networks with distances and so on. You could compute shortest distances and basically travel times by travel distances if you know the speed of traveling. So that is doable. There are ways of doing that, but maybe they're not exactly what you have in mind. But there's quite a bit of going on of network analysis for people who look at transportation networks. So yeah, packages. Okay, so I was talking about models, and here we have the wind turbines. You're welcome. The wind turbine data sets, where I said here this is for a backdrop, and now start plotting that, and then add the geometry of the wind turbines a little bit smaller so that it's not all too occupied. Here you see the locations of the wind turbines. And you see it's scattered, but there are also gaps and so on, and sort of looks at like clusters. And there are different ways in which you can look at it. We looked at the S3 sort of way of doing this, and I think you can zoom. Doesn't really respond to my attempts to zoom it. I can click in any case on things, and I get this little table of the. I can't even read it without glasses. But you can get this table. Similar things you can do with MapView, which is basically a front end to Leaflet. You can zoom a little bit so we can see the individual points and click on an individual point, and you get a similar table. And this all in sort of simple HTML form that directly fits in your notebook. What you also see from this is that we have certain points that are lighter and other points that are darker. And basically we see this dark color is used, but it's used in a transparent way. So if we see a symbol like this that is dark, it really means that there are several points that plot to the same shape, the same symbol, but they basically overlap exactly with each other. So if we click on one of them, that doesn't mean that we see that there are several of them. Yeah? This doesn't have this feature of points that are clumped together that are sort of indicated with a number. Maybe we could do that, but I don't know. I don't know in any case how to do that with R. I would be surprised if it's not possible. We can analyze point patterns by right. So I should start with saying what a point pattern is, right? Where do I do that? A point pattern is basically a process where you have locations of things and where the locations are of prime interest. Yeah, so our interest is now wind turbines. They are things, they have a location. Yeah, so we are interested in where are these wind turbines, why are they there? Is this a sort of irregular? Is this a completely random process? Is this a clustered process? How do we describe sort of the spatial pattern of these points? This is what point pattern is occupied with. So when we try to, basically the go-to package for spatial point pattern is the package Spatial, which used to be a very large package, is now be cut in several sub-packages that are all loaded if you load Spatial. We can try to convert this wind turbine object to a Spatial object. Spatial objects need a window. Yes, they need to tell you need to tell. So in addition to the points, you need to tell them that these points come from this red lined area here. If I wouldn't do that, it would basically assume that they come from the box that encloses these points, yeah, which is not the case, which would mean that this area is empty, but it's empty because it's a different country. These are German wind turbines, right? So it doesn't make sense to consider these points outside of Germany because that was the selection primarily. In point patterns, it's important to acknowledge that sort of because we're going to look at distances, looking at gaps and holes and things like that. And if we do that outside of our window of observation, then it doesn't make sense because it's supposed to be empty because it is not in our window of observation. So point patterns have a window of observation, and that is a critical thing there. So we try to make a PPP, a spot point process, using an object that has this window as first feature and then has a sequence of points. So we get this window basically, and then all these points. And but it gives an error. It said only projected coordinates may be converted to spot.class class objects. And oops. So we have this this object here. Yeah, we read it by read SF. It didn't tell us anything, but I can basically run it. Right, and you see that that it has a geodetic coordinate reference system that is associated to WGS84. So these are ellipsoidal coordinates, right? Spotstat only does things on two-dimensional sort of Cartesian space. So if you have angles, it's not going to work. It's not going to, yeah, so that is a good thing. It's going to warn you, you shouldn't do this. With this data, with these coordinates, you cannot use Spotstat. Right? You can use other things, but not Spotstat. So what we have to do is go through some projection. Here I pretty arbitrarily took UTM zone 23 north. This is not, I arbitrarily took UTM and then took the appropriate zone for Germany. Yeah, there's a couple of UTM zones, but this one is kind of in the middle. So we are just using this one for the whole of Germany, right? And that has EPSG, blah, 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 as a code. You can look these things up. You can also use a proj string and say proj is UTM, and then zone is 23 north or something like that. So it is a string that you can remember. These are not the things that you tend to remember. I always look it up. And then we transform this thing, yeah, and then we can say, okay, convert it to a PPP, and then it does it. It just gives a warning. It says 70 points were rejected as lying outside the window. Yeah, that is happening. Like here, you can see points outside, right? And there might be more, right? So it is kind of just, you know, just offshore or something like that, or generalizations of the country boundary that are too coarse and so on. Of course, we try to put things on the boundary, right? As a country like nuclear reactors and so on. Countries do that, as well as wind turbines. Although these were the onshore wind turbines, right? This is what I try to find. And also it says data contain duplicated points. We already noted that from the map view, that we have points that are multiple times with identical coordinates, right? And here it says they're really identical. They have duplicate points. Things that point patterns can look at are, for instance, density of points, right? Here is a density. Not sure if this argument is going to work. I don't think it does anything. Should have removed that, but this is, I think, the default density of the wind turbines that I get, and it computes a density. Yeah, so that's a great thing. It basically is a measure that says the number of points per unit area. Yeah, so this is the number of wind turbines per square meter, because in UTM my spatial unit of coordinates are meters. Yeah, so this is density per square meter. And that looks great. So if we look at this map, yeah, it's less here, it's more here, and yeah, could well be, yeah. But of course, this is a modeling exercise. This densities just takes a kernel density with a Gaussian kernel by default. You can choose another kernel. You can choose another bandwidth, right? And densities, of course, look different when you do different bandwidths. So this could be a density. I could also pick the density much smaller and say here, this is by using sigma at 10 kilometers. I kind of would get this. Sigma is then the standard deviation of the Gaussian kernel, right? Which is a distance measure, right? So a 10 kilometer is then the whatever, 80 to 70% sort of density of this. And you see that this is a much more wildly varying sort of pattern that I get. And if I, on the other end, of course, take a sigma that's very large, for instance, 1,000 kilometers, then I get something that's much smoother, right? It basically is a sort of kind of a linear trend. And you also see that it hardly varies anymore, right? So this goes from 1.4 to essentially 1.5. Yeah, so there's hardly any variation. You see variation, but it's nearly flat. It's a flat, nearly slightly tilted, but nearly flat density surface. So what does it mean, right? It's not like one is necessarily better as the other. You could do iterative estimates of the optimal density, bandwidth, and so on. So there's different ways you can do with that. And another thing is that you can, with spots, that you can create models that models for the density that basically model the density as depending on other variables, right? And do significant tests on these models. So if there's another variable like population density, then you could use that. And you could say, well, let's see if wind turbines are there where population density is lower, right? Is what you would expect, because they are always placed in the sparsely populated areas. So you could use that and do some modeling. I should have done that. Other things that point patterns worry about, look at, is second order moments, which basically means the interaction of points with other points. Like, are these points randomly distributed? That would mean that there is no interaction, that any point is basically completely by coincidence there and not sort of in particularly more often in the neighborhood of another point or less often in the neighborhood from another point. One way to look at that is with the function kst. The k function counts for a varying window size r, how many additional points are found within the window of radius r centered at each point, and compares that to a completely spatially random process. Yeah, so we do this, we count for different radii around existing points, how often other points are there, and do that also for a process that we generate when it was entirely completely spatially random. And we see here that the red line is the Poisson, is the completely spatially random. And what we observe is the black line is a different curve that says that we basically have more often, that we have more points within every radius than expected, right? For a given radius, we are always above the value expected with completely spatial random. So that means that we have something that is more clustered than if it was completely independent. We can also build envelopes about it, but I didn't do that because it took quite long to run. But you could do that if you put it on overnight or so. Another thing is the G function, often used, that estimates the nearest neighbor distribution function from a point pattern. So the nearest neighbor distance, yeah, the nearest neighbor distances for every point. You see that here, this is the Poisson process, and this is the process we have, and we see there an incredible amount of zero distances. And it is basically because of all the duplicates that we have, right? Every point is sort of, a lot of points have identical other points at the same location, and we get a lot of zero distance in this. We can essentially remove that by using the function, the method unique on this point process, which basically filters out all duplicates. Yeah, so it removes all the duplicate points, and then we see a much smoother point without this point mass at zero. But we still see a strong evidence of clustering, that for a certain R we have many more points with 2000 as a nearest neighbor distance. And for this process, we can compute an envelope very quickly, where we basically do this, and we have this Poisson process, and then generate 99 random processes, and sort of computed the confidence envelope for this Poisson process, and we see that our sampling our sample process, wind turbine process, is not within this envelope. So overall, it's everywhere sort of clearly more clustered than expected when it was independent. So these are points. These are things that you do with a point process. Things you do with geostatistical data are entirely different. So geostatistical data is often focused on the interpolation of a spatially continuous process, yeah, a spatially continuous variable. So doing that, you really need to realize, is my variable that I'm looking at, is it a continuous variable or not? So we could, for instance, look at the power of the Gesamtleistung in megawatts of these wind turbines and plot them, and we could see, well, can we interpolate this, right? Well, this is plotted on a log scale, but nevertheless, you could do it. Actually, you could do it, and something would come out, right? The question is when you would do that, whether something useful would come out, something that's meaningful. So, as I said, we can theoretically interpolate this, but it would be rather meaningless. Because if we basically, for instance, here would interpolate a value, it would be a power of a wind turbine that's not there, right? So there are no wind turbines. These are all the wind turbines. And interpolating this would basically mean estimating values for locations where there are no wind turbines. Yeah, so this is something that while we have a point pattern, we basically have all the points, and in the white space between, there are no points. Yeah, so the points are basically the population, right? Predicting this is not saying something, right? You could try and think that wind power is a continuous variable that varies, but you don't have the wind power. You have just the power of the turbines where the size of the turbine is included. So the size of the so it doesn't say anything about sort of wind potential or so. If you would have wind potential estimates on all these points, you could interpolate those potentially, right? That would not be stupid. But interpolating basically the power of these wind turbines is something that would not be useful. As an alternative, we took here NO2 air quality measurements distributed over Germany, taken from rural background stations. So meaning that they really sort of measure the regional values rather than urban traffic stations, which measure the worst places in cities, right? And they don't make sense to interpolate because we don't have urban street canyons between two cities or something like that. So this is rural background, which makes some sense to interpolate at least. It's a rather sparse data set. It's created in chapter 13 of the book, and here I download it from GitHub, where it's now incorporated in this package GStat, and create an SF object from this CSV file, where we also have to say what is the longitude, what's the name of longitude and latitude columns, and basically state the coordinate reference system. We can then see the data. And what we then do is essentially look at the spatial correlation. One way to look at spatial correlation is compute a variogram. Variograms look at basically pairwise differences and square them and average them and do that for different distance classes. So if something is very strongly spatially correlated, difference tend to be small, their squares tend to be small, and we have a low value. If they're uncorrelated, there is more variability, distance are large, and we have something that increases. So we see an increasing curve. So these are the sample estimates from the sample data with very low number of points of pairs for the short distances. Anyway, a very noisy process, but we can basically say that this is the variance of the process, and we can say that it decreases, and whether it's, whether it really goes to zero is pretty opportunistic, but let's do it. It generates nice maps in any case. Yeah, so this is like the flipped version of an auto covariogram, right? Which is an unscaled version of an auto correlogram, right? Which we know from time series. It's very much related. It's just flipped the sort of y-axis is sign flipped. Then we can create a grid over. We can create a regular grid over Germany, which just takes some grid sizes, and so it's not so incredibly important. And we can carry out a kriging here, which takes a formula for the model, which basically says NO2 is my response variable, and I have a constant mean. The data are resolved from this data set, and these are my target locations. My spatial autocorrelation is sort of reflected by this curve, and this curve is essentially obtained from this little data frame, which has these parameters of the curve. And then I can plot this and basically get this grayscale plot of the predicted, the interpolated values of the NO2 variable. And on top of that, I plotted the boundary of Germany and the locations of the measurement points. You see that all sort of the maxima of this whole field, maxima and minima, all kind of follow nicely the pattern of the observation. So it's really a smooth surface that goes through the minimum and maximum observations and follows that in a relatively smooth way. Now you see that I kind of also interpolated here, and in principle you can do this because air quality doesn't stop at boundaries. It's a continuous process. Of course, it would have been nice to use the observations of Czech Republic if they are there. I should have done that. It would have given a more complete picture. But it's not like the process stops here. Yes, like densities with wind turbines. Right? That I would have to stop at the boundary, but this is continuous. I can do it. It's not, you shouldn't exaggerate, but it's not like I should cut it off. I can of course cut it off, like here. Oh, sorry, this was going on here. All right, this was another note. Yeah, I can cut it off and get something like this. Yeah, which is also okay, which is more commonly done maybe. Yeah, but not essentially necessary. What I did here was another thing. Here you saw that I had my distances in kilometers and had my my observations all in degrees, latitude, longitude. So I worked with ellipsoidal coordinates, and the software understood it and worked with kilometers and used proper distances and a proper covariance distances and so on. Usually it's a better idea to do everything in projected space, and I can do that here just to make sure that you can do this. So I can transform the boundary, I can transform the points, I can then create a new stars object. Here you see I have distance in meters because it's projected and my coordinates are now meters. And I can do the projection again. You see very different values. These are the UTM coordinates of my new grid, which is everything in UTM. But if you look at the two images, it is very similar what you get out because it's a relatively small region. So the curvature of the Earth is not doesn't have a big effect in whether you take it as flat or you take it as curved for an area of this size. Finally, my last point I wanted to come to is lattice data, and I really strongly recommend to you, if you want to learn about that, is to read chapters 14 to 17 of the Spatial Data Science book that I authored with Roger Bivand. In particular, because Roger is the author of these of all these chapters that deal with aerial data, and he's much more a specialist in that than I am. But a couple of examples that I took essentially from the book and gave here as a sort of summary of things that you can do. Here we'll look at a data set from the SP Data Large package. Here are instructions to install that package. And these are voting wards. Yes, these are first round turnout proportion of registered voters in municipalities in Warsaw boroughs in the 2015 Polish presidential elections. Yeah, so here are all these wards plotted with the package TMAP. We haven't seen TMAP so far, but TMAP is a package that uses syntax very similar to ggplot, but is entirely independent and does a very good job in creating high quality presentation graphics. Here we have basically aerial data, and we're looking at we're basically looking at voting turnouts, and we're computing Morans I, which is basically a correlation coefficient that looks at whether to what extent neighboring regions are correlated, yeah, and looks at basically the differences between regions or the product of values in regions, centered product, compared to overall variable levels of variability. And for this, it needs basically a data structure which tells which area has which other areas as neighbor. Yeah, so it uses here the poly to neighborhood. So this takes polygons and creates a neighborhood objects, which is here, that tells me basically does for each polygon looks, you know, are these two polygons neighbors? Do they have the shared polygon boundary polygon points in common? And converts that into a list W object, which is called LWQB, and that is used in the moron.test routine, which basically looks, which uses this neighborhood list, which uses the original data for the attributes, and then does the Moran's I test. Yeah, and Moran's I statistic, you can see here, you can compare that to a correlation coefficients, is 0.7. The expectation is 0.00. The variance is very small, so we get a z value, the standard Z distribution we assume here, Z value of 60, which has a p value of 0, which means this is highly correlated, highly spatially correlated process. Right, so this is a Moran I that is used a lot, and the chapter gives a lot of alternatives to this. For instance, doing local Moran I tests and things like that. And then if things are spatially correlated, you can continue and do spatial regression models that basically extend standard linear models by taking spatial processes into effect, and do that typically by two different ways. Either they include a spatially correlated residual, so an error process, or they include a spatial autoregressive process. Yes, that means that the response variable is put in a spatially lagged fashion, put in the design matrix, put in as one of the predictors, and basically do a spatial auto regression model, like in car models, conditionally autoregressive, or SAR models, sequentially autoregressive models. And there are several examples in chapter 16 and 17 that do this, and that use all kind of different maximum likelihood, method of moments estimators, Bayesian estimators using MCMC, Bayesian estimators using integrated nested Laplace approximations. All these kind of examples are carried out in chapter 16 and 17 and compared. Yeah, so you can use these data sets and reproduce them and plug in your own data. A thing that is not mentioned in the book, regrettably, is or maybe not, you know, at some stage books get too thick, are panel linear models and spatial panel linear models. Panel models basically look at time series for individuals, right? Everyone knows panel models probably. You know them much better than I do. There is a package in R called PLM for panel linear models, and you could, for instance, with the Gapminder, and I have no clue whether this makes sense in the way I now sort of describe these models, but you can use the Gapminder data set, yeah, which is essentially a long table where data are indexed by country and year. Country is then the first index, is the item, the subject, and year is the second index, is basically the time replicate of observation. So we have time replicates. Panel data means we have time replicates of items, of individuals, of regions, or whatever. Yeah, in this case, it is regions. And we have a panel model where we basically model life expectancy as a function, linear function of GDP per capita, right? And this does this panel model, and essentially basically takes into account the time structure of these data. PLM has all kind of different ways or different models, and you're doing different ways of including the time effect in your modeling approach. A package that extends this is the package SPLM that has been published and described in this paper, SPLM paper, Journal of Statistical Software, in 2012 already. That are spatial panel data models that essentially does the same type of modeling, but does it in a spatial context, right? In panel models, in principle, the items you have, the subjects are considered independent, right? There is no way that PLM is informed that countries might have another relationship to another country because it's not there, right? There's just a country, it's just a label, it's just different. And SPLM does that and basically uses here. We say we're going to filter this for a particular year, and then we're going to say which intersections do we have, which country intersects with another, meaning that which country touches another one is in this case the case. And then we're going to use that. Basically, we have an incidence matrix, which is a logical matrix, true or false. And then we're going to replace the diagonal with 0 so that all the self-intersections are removed, because of course every country intersects with itself, that we're not interested in that. And we're going to row standardize this thing. So we're basically going to divide by the sum of the row elements to get an incidence matrix. And then we still have to remove all the things with 0 neighbors, right? Because, for instance, countries which are islands or Australia or something like that are basically don't have neighbors, so we don't have relationships. We don't find any relationships by using intersections. We could, of course, use as an alternative. We could use distances between countries and row standardize them. For instance, the distances to the 10 nearest other countries or something like that. We could have used that as an alternative. We're now using whether countries touch, and that means that we have to deselect also in our analysis the countries that have no neighbors. And I also have to drop the continent variable so that columns 1 and 2 are the individuals. And then I can use a spatial linear model where I use the same model, same equation, and it's a reduced data set because I had to throw out all the countries that had no neighbors, but using here a list W that indicates the spatial effects. Yeah, so the spatial effects of the countries that have neighbors, and that will then be taken into account. And you can see here that that we get the regression estimator, yeah, the regression table with the estimated effect of GDP per capita, which is 0.03, and it used to be 0.16, so that's pretty much higher in our new model. But we also have an estimate of the spatial error parameter, yeah, which is essentially a correlation of the residual, spatial correlation of the residual based on based on being neighbors with another country, right? And that is also considered significant. And we can make more complicated models, for instance, by including, in addition to an error effect, including a lagged effect. So we have both a spatial correlation here, which is now negative, interestingly, which was strongly positive here, because we included an autoregressive effect, which is now also strongly significant, right? And we have an effect of our model 0.04, which is relatively closely to the effect when we only had a spatially correlated error effect. And so these are things you can do with panel data and with spatial panel data, and there are packages to do that and routines in SF that help you find out whether polygons touch each other, whether polygons are neighbors, or even to compute distances between countries and use distance-based spatial relationships that you could use as an alternative in these kind of models. So that brings me basically to the end of my slides. I hope you liked my slides. I mean, they were created essentially for you to be able to easily redo this and use these kind of things as a starting point for your own analysis. This is also exactly the way this whole book that I mentioned at the start was being set up with reproducible examples. And I hope you enjoyed this, and I look forward to your questions. So are there any questions left? I realize that I left you very little time.
Hi, Edzer. We have a couple questions from YouTube.
Very good. Go ahead.
Is it necessary to row standardize? I wonder if it's okay not to do so if I assume the neighborhood relationship to be symmetric. And row standardization doesn't preserve that if neighbors have different numbers of neighbors.
Yeah, that is a good question. Actually, I have to say that I'm not enough an expert in these kind of models to give a comprehensive answer to that. What I remember from this row standardization is that certain models require it and others don't. From the top of my head, I thought that car models, for instance, require it and SAR models don't, something like that. So you really need to look into the literature and look into examples, people using examples and explaining why this is needed or why this isn't needed. This is a little bit beyond my sort of area of complete understanding. Are there any other questions from the YouTube channel? This was a nasty one. No, a very good one, I mean.
Nothing so far. I directed other stuff already to the chat in the Zoom, so nothing here. Yeah.
Well, if there are, if there are no further questions, I think with an eye on the clock, we are kind of got to the end of the workshop. So I suggest, I hope that you learned something from this. I will hang around in the Zoom. So if you want to sort of, drop by and ask something directly without everyone listening or watching, hopefully the YouTube channel will be shut off shortly. Then I can still answer questions in a more informal manner if you want to. So thank you for participating.
Thank you very much. Lots of gratitude in the chat here and on YouTube. Thanks a lot, Edzer.
Okay, well, you're welcome. It's my pleasure. Okay, I see we're streaming. Olga, I see we're still streaming live. So I think the best is that I hang up then as well, right?
Yes, I'm going to end session for everyone. And if someone wants, they maybe can send a message in the Slack channel or send them an email to us. So if someone will have other questions. But thank you so much, Edzer.
Okay, it's my pleasure. Good. Have a nice day.